This is Webtalk 6 in the Mplus Webtalk series. It covers dynamic structural equation modeling, commonly referred to as DSEM. My colleague Timer Asparov has done an incredible job developing the statistics, the algorithms, and the code, and has taught me a lot about this topic. We would like to acknowledge helpful input from Ellen Hammacher as well as Luz Kaisers, who provided the data for the example that's used throughout the talk. We also want to thank our Mplus team members, Twee and Noah. It has been 6 years since DSEM was introduced in Mplus version 8.0, and there are now many tutorials on the topic. Here are some of them. On the Mplus homepage, in the right column, we have the Mplus short courses. We have 13 topics, recorded most of them at Johns Hopkins. And in August 2017, we recorded topics 11, 12, and 13, whereof topics 12 and 13 have to do with DSEM. So I recommend that. DSEM draws on Bayesian analysis, which is also covered in these short course videos, for instance topic 9 and also as part of topic 11. On the home page you also find a new tutorial video series on DSEM, which is made by Ellen Hammacher. It's a shorter form of presentations and in a different style. In the leftmost column, you also find the Mplus special topic of DSEM with its many papers that have been written so far, DSEM and RDSEM theory here, starting with the 2018 paper that began the whole story and going forward to more recent papers. You also find a list of DSEM applications. And if you have a good paper that you just finished, send it to us so we can consider posting it on the website. The goal of this web talk is to present DSEM in the way I currently view the topic, the framework that I draw on to understand it, and the steps I take in doing a DSEM analysis. The web talk also presents several new DSEM features made available in Mplus version 8.9. These include random covariances for two-level and cross-classified analysis, new settings, as well as new plot options. All in all, this web talk weaves together 3 different strands: the analysis of the example, including interpretation of results, the statistical aspects of DSEM, and the Mplus features that are available with DSEM. On slide 2, you find the outline. Here I introduce the example, which has to do with mood profiles related to depression in adolescents, with variables such as positive affect and negative affect. In section 2, we're going to talk about a common issue with DSEM type data, intensive longitudinal data, with varying times of measurements, actually random times of measurements. And the handling of that is done by the T-interval option in Mplus, and I'm going to give a little bit more detailed discussion of the practical aspects of T-interval in this talk than what you have seen elsewhere. And this understanding of this option is also useful for creating time manually on your own. In section 3 then, I start with the first step of the analysis that I suggest that you should do, namely descriptive analysis to understand the data, by a simple 2-level basic analysis, where you can take a look at the histograms of the variables so that you can check that you get what you expect. In section 4, I turn to a second step. I'm going to do 2-level analysis, regular 2-level analysis, or 2-level random analysis, where I'm going to take a look at the estimation of intra-class correlations and bring in the new topics of random covariance, as well as the already existing topic of random variance. In section 5 then, on slide 3, I turn to the DSEM topic in itself. So we start with a two-level analysis where we bring time into the model explicitly. And that's via the t-interval option. And I'm proposing here to first look at univariate DSEM, one variable, to get to know it and understand how you should model it before you start a very complicated model. I'm going to discuss various ways of drawing model diagrams, taking a look at some equations, and then also Mplus input and plots. And the next step then is two-level DSEM and residual DSEM in the bivariate case. So you could look at so-called vector autoregressive models, cross-lag models of the DSEM and RDSEM kind. In section 7, I go to take a quick look at categorical outcomes. Going to look at a binary version of the negative affect variable. In section 8, I look at a cross-classified analysis as the last step in the DSEM analysis sequence. So cross-classified DSEM, where we take a look at trends over time. I'm not going to go deep into that topic. I'm going to save that for a later web talk. In section 9 then, I discuss how large the sample size and the number of time terms have to be. First, I do a simple checklist of suggestions that you may want to take a look at. And then I also propose that you might want to do your own Monte Carlo simulation to answer the question about N and T. And I show you Monte Carlo input for both two-level and cross-classified DSEM. Turn to slide 4. I will introduce the example in this section, the example that will be used throughout the whole talk. Slide 5 shows the so-called grumpy or depressed data, which comes from a study of at-risk mood profiles related to depression. So these are data that are obtained by ESM questionnaires measuring positive and negative affect in Dutch adolescents. So the ages are 12 to 16 and 63% are girls. We're going to take a look at positive and negative affect, these common measures in psychology. And they're each measured as an average of 6-7 category items. We also have a third variable, tiredness, which is measured on a 7-point scale. Sample size is 240, and there's several measures per day for 7 days in a row, Tuesday through Monday. We also have some covariates that we're going to use, gender and the so-called SDQ measure, which is a measure of childhood emotional problems. You can read more about the study in this article. On slide 6 then, I point out that the ESM questionnaires were filled out throughout the day, including during school hours. And they were delivered on their smartphones. 8 measurements, well, there were supposed to be 8 measurements. We'll see it's a little bit different than that. It's supposed to be taken randomly in 3 blocks of time between 8 in the morning and 10 at night. So 1 morning measurement between 8 and 10, and 6 measurements between 10 and 8, randomly dispersed through the day. And then an evening measurement between 8 and 10. Turn to slide 7 then, section 2. How do we handle varying times of measurements that arise by these random measurement times? Slide 8, we're starting to move towards the Mplus option t-interval, which is needed because times of measurements are not the same across people. Data are misaligned with respect to time due to this random measurement occasion feature. Now, of course, varying times of observations are common in longitudinal data, but it needs special attention in DSEM due to using lagged effects in DSEM. And lagged effects, by that we mean that we focus on we use in the model the time distance between the measurements at time t minus 1 and time t, needing that to be the same across people. So the distance means the same thing. Not 1 hour for one person and 3 hours for another person. And this can be accomplished by inserting missing data rows in the data set to align time. That's what the t-interval option does. I'm going to show you two hypothetical examples, and then we'll take a look at the real data. On slide 9, you have a first hypothetical case with frequent measurements. So let's take our time to look at this. First we have the original data, and then to the right we have the aligned data that we're going to use for analysis. So for the original data, we will look at two people, ID1 and ID2. And for each of them, we have a time measure, hours, and an outcome, which we'll just call Y. And then we look at the data rows. And for ID1, we measure that person at 9 in the morning, 10 in the morning, and 11, and at 1 in the afternoon. So we have 4 measures for that person. For the second person, however, we have measurements at 9, 11, and 12. So only 1 is common with the first person. So what we do is to align the data so that we insert a missing data row for an hour that observed data is not available. So for ID equals 2, we don't have 10 o'clock for that person, so we put missingness here. ID equals 2 is measured at 9 and 11, but not at 10, whereas 10 o'clock had a measurement for ID equals 1. Likewise, we insert missing data, these asterisks, for the hour 13, for the hour 12 for the first person, because we only observed time 11 and 13. And for the second person, we include missing data for hour 13. So quite straightforward. So the first person gets 1 missing data row, and the second person gets 2 missing data rows. So this is insertion of missing data rows using a time interval of 1, which is obtained by the variable command option t-interval, t parenthesis 1, where t is the name of the time variable. So for instance, the hour here that we were working with. And the data row will then be what we would call a bin number, the time that's actually used in the analysis, this integer time, 1, 2, 3, 4, 5. On slide 10, we have a second hypothetical case, in this case, infrequent measurements. So with infrequent measurements, time interval 1 would give many missing data rows. So if you look at this original data set here, we observe somebody at the hour of 9, 13, 16, 19, and 21. So with 1 hour time interval, we would have missing data rows for 10 o'clock, 11, and 12, and then 14 and 15, and then 17 and 18, and then 20. So that would be quite a few missing data rows. If instead we use a wider time interval, like 2, we have the bin range from 9 to 10 here. We have somebody in that bin, this person. 11 to 12, we don't have anybody, so we have missing. 13 to 14, we have this 13 person. And 15 to 16, we have somebody. 17 to 18, we don't have anybody. And 19 to 20 and 21 to 22, we have an observation. So here we would end up with only 2 missing data rows, as opposed to many by inserting all of the missing hours under the time interval 1 situation. Now for the grumpy or depressed data, on slide 11. Let's take a look at that. So the total number of hours for this study is 24 hours times 7 days, 168. Now the smaller the time interval, the better the match to the data, but the more missing data is inserted. So here we have for this data set, I think we have 3 candidates for time interval. Time interval 1, time interval 2, and 3. If you choose 1, then we get 24 time points per day, 1 for each hour. Maximum number of time points will be 168. And the coverage then is 0.17, coverage being the proportion not missing. So fairly low coverage. Can handle it, but for some more complex models, that's going to give problems. Time interval 2 gives 12 hours per day, 12 time points. Maximum number of time points then is 84, coverage 0.341. Much better coverage. Time interval 3 gives 8 time points per day, which was actually the aim of the study. Maximum number of time points then is 56 with coverage 0.507. Usually we want much more coverage when we analyze data, but in this case low coverage works fine, except perhaps when it goes down to very low values. So now let's look at the real example here. A person number 41, and let's consider time interval 3, so 3 hours. So you have then, starting with the bin range 0 to 2 here. So this is after midnight. So the bin range is 3 here, 0, 1, 2. And the midpoint is then, since the bin range is 3, midpoint is 1.5. And if you add 1.5 to 0, you get 1.5. So that's the new time midpoint of the bin range, which we're going to use not for the analysis, but to gauge how misaligned the data is. Now, if you take a look at then observed times 7 and 8 in the morning, we have the bin range 6 to 8, and it falls in, so 2 time points that are observed are falling into one and the same bin range. And we don't want that. We don't want several people in the same bin. So you spread them out in Mplus. If you take the average, you would get a change in the precision of the measurements, which is not something you want. So we put 7 into an earlier bin and keep 8 in the same bin. So you get a slight misalignment there. The midpoint is 4.5 here for that bin, and we're saying, so that's between 4 and 5 in the morning, and we give the 7 o'clock measurement, see that as an earlier measurement. So some misalignment there. Now look at 12 and 14. Here we have to do a more elaborate scheme. We have to move 14 down to the next bin and then move 16 and 18 further forward. This is all happening because we have a very wide time interval of 3 here. Perhaps not desirable for this person. So for this person who was observed at time 18, 6 in the evening, and that person gets misaligned to fall into the bin range 21 to 23, so about 10 o'clock at night. So the distance here then with the which is used to gauge the misalignment issue is 4.5 for that person. And we have information in the plot output about this kind of misalignment per person and overall across persons for different time interval choices. So you have to decide yourself from a substantive point of view, is this an important deviation? How you feel positive affect or negative affect at 6. Does that distort the picture if you pretend that happens at 10 in the evening? Or is that not important? and also to see how often does it happen, how many people does it happen for. Perhaps it's ignorable because of that. Now, and you can continue to the next day's morning here, 7, 8 in the morning, and we have to move one person into an earlier category. Two things here, technical. The range is more precisely stated as from 21, greater than or equal to 21 to 24. I'm looking at this here, this range. 21 to 23 is what we say, but it's more correct to say 21 to 24, where 24 is not included, when time is not even hours, when there's fractional time. That would be a more precise way of stating it. And the principle is, again, if there's more than one observed time per bin, rearrange observed time into neighboring bins. One move due to bin 3, up here, that's one move, and 3 moves due to bin 5. Bin 5 moves 14, which then moves 16 and 18 as well. So 4 out of 8 observed times are misaligned in the first day for person 41. 7, 14, 16, and 18. So there's something for you to sit and think about. And misalignment quantification is this SMSE measure, square root of mean squared error, simply the distance in hours. Now, let's take the same person, but time interval 2. So a smaller time interval. And for the bin range, we only have one observed time for each and every bin range. Perfect alignment, no need to rearrange observed time. So there, it doesn't hurt the data at all. But if you go to, that was person 41, if you go to slide 14 and person 20, then you will have, with that same time interval 2, you will have 2 measurements falling into one bin, and you have to move the one measurement to an earlier empty slot, so one misalignment. Now, for day 2, then you would have 2 misalignments. You have to move twice here. You have to move 36 up to earlier, 38 into 36's former position, and keep 39 in the same spot. So this gives you a flavor of what Mplus does for different time intervals, and perhaps also ideas for how you might want to manually score your time to align to synchronize people's times. Maybe your manually aligned time does a better job than what Mplus automatically does, but as we will see in analysis to come, in 2 places I have compared the results when using T interval 1, 2, and 3, and there are not important differences. In section 3, we're going to take a look at descriptive analysis to understand the data using type equals Twolevel basic. First, on slide 17, let's remind ourselves about the data structure. Data are going to be in long format, so we have time nested in individuals. And here we show the 3 key columns in the data: ID, hours, and the positive affect score. So for person 1, we observe him or her 1, 2, 3, 4 times at hours 9, 10, 11, 13. And then person 2, observe that times 9 and 11, followed by person 3, etc. I'm going to propose that we do 5 steps in our analysis to understand the data better. Step 1, which we're talking about here, it's going to be a 2-level basic analysis to check histograms for the variables and within and between level variation and between level plots. We can use maximum likelihood with robust standard errors and chi-square for that. Step equals 2. It's going to be then a 2-level analysis, a modeling activity. 2-level or 2-level random. And we're going to model the variation in the mean, in the variance, and in the correlations. That's the new feature. Using then the base estimator. And I'm going to refer to that as regular 2-level analysis, as opposed to what we do in step number 3. which is a perhaps a two-level random DSEM analysis where we bring time into the picture. That's also going to be by using the Bayes estimator. I'm going to start with a univariate analysis, which I think is useful to understand how the data behaves before we go into complex models, as in step 4, where we do the same type of analysis but for the bivariate case. So bringing in more variables, then go on multivariate if that's what's called for. And finally then in step 5, turning to type equals cross-classified analysis. So cross-classified DSEM instead of two-level DSEM, still using the Bayes estimator. On slide 18 then, here's step 1, the two-level basic analysis. We're going to take a look at positive affect, negative affect, and also the tired variable, as well as the hours variable. And this is sort of a basic first analysis, which helps make sure that you're reading the data correctly, which is a fundamental error that is made quite often in our experience. So we have two-level analysis, two-level basic analysis. We have to give a cluster variable, that cluster equals ID, and we're going to do a lot of plotting, so we use type equals plot 3. In the output then we get a warning that one or more individual level variables have no variation within a cluster, and then it lists the clusters. So those individuals have limited value for the analysis, and we're going to be particularly interested in deleting them when we get to DSEM modeling. So these individuals may be deleted, and we're going to talk about that more in detail later. For now, we're going to keep them in the analysis. Here's a summary of the data that's printed in the output. We have 240 individuals, and so we have the cluster IDs and ordered by size of the clusters. That is, in this case, how many time points they have. It's 1 through 24, continuing 25 to 49. And the average seems to be around 24 time points. And we recognize then if you go back one slide here, the first positive affect cluster that had no within cluster variation was 240. Go back to slide 819. 240 is bolded here. That person had only 2 time points for which they gave the same PA answer. That's a person that you don't get much value from in terms of the overall analysis. And we also have slide at ID 249, which has 3 time points with equal values, and then ID 78 with 4, and ID 531 with 5. 531 was the last one of the 4. So 5 time points with equal value, those individuals could be safely deleted. Individual 45 is bolded for another reason that we get to in the in subsequent analysis. So here is our first result on slide 20. We get the so-called estimated interclass correlations out of the type equals basic analysis. So we have an interclass correlation for PA, for NA, and for tired. And the correlation is about 0.5. What is it? Well, it's really a variance ratio, the variance between individuals over the total variance between plus within individuals. Now, variation across or between individuals is viewed as a variation of a random mean. So you think about a variable that corresponds to an individual's or to the individual's mean across time. So each individual has a mean across time, and that mean varies across individuals. So variation in the average level. So a trait variable or a response style variable. Different people have different average over time of their positive affect or negative affect. But they, in addition, then we have variation across time for the individuals. And why is this important? Well, it has to do with how much variance in the outcome that this so-called trait variable contributes. So it is the contribution of the variance between variance relative to the total variance. So it's the R square of the trait in the regression of the observed variable on the trait. So it's a very key quantity that we're interested in. And it's often quite high, but often around 0.5 at least. But there certainly is more variation than that. There's still within variation that's substantial. Slide 21, then we take a look at some histogram plots. And for the positive affect variable, we see that it's quite skewed. We have a ceiling effect at the highest possible value, 22%. My rule of thumb is that you want to do something else than linear regression or linear models when the ceiling effect exceeds, say, 25%. So here it's not quite that bad, so it wouldn't hurt us too much by treating it as a regular, continuous, approximately normal variable. Now for the negative affect, it looks much worse. We have 60% at the floor effect. So here you would not want to go ahead and just treat it as a continuous variable and expect to get results that are trustworthy, because the regular models that we use are not designed for variables that have that strong of a floor effect. For the tired variable, we have 23% floor effect, and again, that's, to me, acceptable. Here's an interesting histogram from this run as well. For the hours variable, I think that's something that you want to look at. So you have a histogram here. For the hours, you see the 1, 2, 3, 4, 5, 6, 7 days. The hours of the 7 days of the week, Tuesday through Monday. And you see that most measurements are in the middle of the days. Here we have the hour of 23, 11 o'clock at night, and a few measurements there. People are coming alive again at 30 hours, namely at 6 o'clock, 6 hours after midnight, coming back. So you can see the coverage of measurements across time here, and you see also a certain tendency to drop out, or at least give fewer answers as time goes on. You also see then that although the maximum time is 168, as we agreed on previous slides, you have observations that are much higher than that, 170 and up to 243. So here are some glitches in the data that you want to check out what happened there. People kept reporting, or some scoring error. So you want to cut off, in your series analysis that follows, you want to have a use observation restriction to only include those with max time 168, not beyond that. Now this histogram actually I got by changing the display properties from the default of 20 bins to 100 bins to see it more clearly. On slide 23 then, we show a between level histogram of the person's average over time. So here's the average over time. So you take each person's average, and that becomes a new variable for across people, so 240 observations, and then you do a histogram of that. So that's done in Mplus, and you see that that variable is much less skewed than the earlier histogram that we looked at for individual values. So now we only have 2% at the max value versus 22%. So that's because the max value over here in B, it is the most common value observed in the data, but it does not mean that it's the most common average value. So two different things. This between-level histogram of averages over time corresponds to the distribution of random intercepts. So the random mean or random intercept, which is assumed to be normal in the between-level part of the model. It's not exactly normal, but it's close enough to not cause serious distortions. On slide 24 then, which is the final part of the first step, we take a look at the between-level scatter plot, and these scatter plots are quite useful. Here it is of the mean over time on the x-axis for positive affect in this case, with the variance on the y-axis, variance for positive affect. And you see then that the variance is quite different, ranging from almost 0 up to 5 here. So there is heteroscedasticity in the variance, difference in the variance, but we also see that there is some negative correlation here between the mean and the variance. So the smaller the average, the mean over time, the larger the variation. So correlation is minus 0.43 in this case. So whatever modeling we do later on, we should try to capture this relationship. For the negative affect, it shows a correlation that's positive, 0.65, and the tired variable shows no correlation at all. Now we turn to regular two-level analysis using type equals Twolevel or Twolevel Random. On slide 26 then, we have step 2 in our 5-step analysis. We're considering two-level modeling. We're going to take a look at all 3 variables, positive affect, negative affect, and tired. And we're going to take a look at 3 different models, the first one being a random mean model. And that's exactly the same kind of situation as in step 1, the two-level basic analysis. But now we're going to carry it out as a modeling activity. So we're going to ask ourselves, what portion of the total variance is due to variation across individuals in their means across time? And we may also want to bring in some predictors of that variation. So we turn to equation 1 here, and I'm going to try to use equations sparingly, because I know not all of you love to look at them, but I'm going to keep the very simple equations. So we have a single outcome, y, measured for individual I at time point t, and we have a random mean that we're going to call alpha with subscript I, so varying across people only, the average value across time, varies across people, not across time, plus a residual epsilon, which varies across both individual and time. So alpha is the random mean, an average over time that varies across individuals, also seen as a latent trait, exactly what we talked about before. And the residual is a normally distributed variable, which is assumed to be uncorrelated across individuals and time, for simplicity to start with. Now, once again, the random mean, thought of as perhaps a latent trait, accounts for correlations across time. You know, same person measured at different time points, those time points observations are going to be correlated. We want to account for that correlation, and it does so, that random mean, because of the interclass correlation being expressed in this way, the between variance over the total variance. The larger the between variance, the larger the variance in this random intercept or random mean, the more correlation across time. And the ICC is the same as the R-square for the variance of the outcome explained by the random mean. That is the R-square due to the latent trait. We can also note that the random mean plays the role of the intercept growth factor in a growth model analyzed in a two-level long format. So if you look at this, a random mean, it's the intercept growth factor. It influences all time points, influences y at all time points with the same invisible 1 unit multiplier 1. So the fixed loadings are 1, as I write here. You can think of it that way if it helps. So on slide 27 we try to express this model 1 in formulas, diagram and input on the same slide. So here's the equation again, and referring to the diagram bottom left here, y is the observed PA variable in this case. It's a square, and alpha is the latent PA variable on the between, it's a circle, and epsilon is the latent PA variable on within, it's a circle. So we think of this as between and within variation, which adds up to the total variation of PA. And we note then, for those of you familiar with cross-lag panel modeling, this is a diagram that's drawn just like a random intercept cross-lag panel model, except here we're just showing one time point. So that model, that kind of drawing is what we're going to build on for DSEM when we get to that. In the right column here you have the Mplus input, and now we notice that we have use observations here. We are actually restricting our individuals to those who have less than 168 time points, or restricting their time points to less than 168, and we are deleting those 4 individuals and that had no change in positive affect across time. We do a 2-level analysis using the base estimator, and this is how I usually do that. B iterations, a minimum of 1000 iterations, and I usually specify 8 processors because my computer allows that. I'm not going to talk much about specifics about base estimation. Instead I refer to those short course topics that I pointed out in the introduction, that is in video format on our website. And it's also covered in our book, Regression and Mediation Analysis in Mplus. The model then is a within and between model, 2-level model, and all we do is label here or mention the variance for PA on within and the variance for PA on between. So we're referring to the within part as this variable and the between part as that variable. And here now we want to compute the ICC. So we use model constraints to form a new variable or new parameter, ICC, which is B divided by B plus W, referring to these parameter labels in the model command. And that gives us a PI ICC estimate of 0.57 with standard error 0.024. And that's the same value, 0.57, same value that we got in the 2-level basic analysis. So here we have also the within estimates and the between estimates listed, which come out in the output. Now let's go to model 2 now, step 2, model 2, where we add the random residual variance. Random variance. How much does the residual variance vary across the individuals? What are its predictors? And what's the correlation between the mean and the residual variance? So still we're considering a single outcome, a random mean and a random residual variance, so alpha sub I. And the residual now is distributed normally with mean 0, but has an I on its variance. So the variance also varies across individuals. And we're going to make an assumption that the logarithm of the variance is normally distributed. And I'm going to talk about that a little bit now and much more later when we get into DSEM analysis. Here's how we draw it. Y is still the observed PA variable. And alpha is the latent PA variable on between. Epsilon is the latent PA variable on within. But now we also have a random residual variance that we mark with a filled circle on within, and which becomes an open circle on between. So a latent continuous variable on between. And now then we have two circles here on between, and we can estimate their correlation. The input for that is on slide 30. The only difference on the left-hand side is that we have now added the random here, because we are going to introduce a random residual variance, and this is something that's existed in Mplus for a while now. So we have log v is the name for that variance, bar PA, defining this random residual epsilon variance. And on between we say that the mean and the variance are covaried, and we're also giving labels for the mean and for the variance. So that the mean and the variance of log v, not the mean and the variance of v. And then you can express the mean of v here as this form is the exponent of the mean and the variance divided by 2. In fact, you can get the median by deleting that second term. So just e to the power of m gives you the median. Now, there's a lot that can be said about log v and how to understand it. Here on slide 31, I just take a first simple stab at it, and then we'll get back to it on slides 65 and 67 in the DSEM context. So here's the basic issue. Bullet 1. So random effects are assumed to be normally distributed in most software, most statistics, and certainly in Mplus. And that's not a suitable assumption for a variance, because a variance, as you know, has a skewed chi-square F distribution-like distribution, and is never negative. So because of that, we're using the log of the variance instead, which is emphasized by calling it log v. So the mean m of the random variance, log v, can therefore be negative because it's on the log scale. Negative values happen for residual variances that are less than 1. Value less than 1, when you take log of that, gets to be negative. We'll see negative values in the output, and that this question often comes up in Mplus support. To get the mean on the regular scale, the log v should be exponentiated like we did in the previous slide. And the correct exponentiation for the mean involves the variance as well over here, which is due to theory of the log normal distribution. So it's a lot of facts here, but it'll become clear. The median is e to the power of m only, and it's probably more useful as a summary if you want a one-point summary, one statistic summary, because we have a skewed distribution of the variance, and the mean then tends to be, we have a long right tail, which implies that the mean is going to be quite far out to the right, and the median is probably better representative. And the mean and the median of the variance can be expressed in multi-constraint like we just did, and multi-constraint then gives you confidence intervals, and if need be, they are non-symmetric automatically by using Bayes. And like I say, a fuller discussion of log v is presented later in connection with step 3 model 2 on slides 65 to 67. So the issue is that means and variances of log v, they don't tell you very much. And translating to means and variances of v doesn't tell you very much either. A better understanding of the range of likely values for the variance, it's a random variance, the range of likely likely values for the variance is through looking at the quartiles, which we can express in Mplus model constraint quite easily, drawing on the mean and the variance of the log normal log V distribution. More on that then later, but first the estimates here, output excerpts rather. So we have on the between level a covariance between PA and log V, which is negative, which corresponds to what we saw in the between level plot for the mean and the variance, a negative relationship. Mean of log V is negative, but you shouldn't worry that it's negative, because we're going to take a look at the e to the power of it, as we did here for the mean, which involves also the variance of it, or just the median, which involves only the mean. And by the way then, since we're on base, the SD, posterior SD column corresponds to the analogous to standard error for maximum likelihood, and the estimate divided by the SD is approximately a z-score, but the confidence interval, 95% confidence interval, is a better statistic to report, and the quantity on estimate is significant if it does not cover 0, which this doesn't, so you get a significance asterisk here. And the correlation, this is covariance between the two. The correlation between the random mean and random log V residual variance is minus 0.2. The scatter plot correlation with the variance between the mean and the variance was minus 0.43. So similar results. Let's go to slide 33. So we go to Model 3. So here's a new feature in version 8.9. We're going to talk about random residual covariance. So the question then is, how much do the residual covariances between different variables vary across individuals, and can we find some predictors of them? So now we're looking at bivariate or multivariate outcome. We can do both in Mplus, where we have not only random means, not only random residual variances, but also random covariance. So the residuals have individually varying variances for the outcome y and for the outcome z, the two outcomes that we're considering. So you have a subscript I on the variance, both variances. And we're going to allow for an individually varying covariance, which is this product of a correlation times the standard deviations. You know, if you multiply a correlation by the standard deviations, you get a covariance. And rho sub I, the correlation, is then transformed by a so-called Fisher transformation to make it into a approximately normally distributed variable with a certain mean and variance. And the technical side of this is described in this technical document, and we'll probably update the year for it. You'll find it here in this URL. So the idea is that the base Markov chain Monte Carlo algorithm likes to work in the correlation metric, but not the correlation per se, but a Fisher transformation of it to make it yet another normally distributed random effects. Just like every other random effect, we want it to be normally distributed. So this Fisher transformation does that. It keeps the variable as varying from minus infinity to plus infinity instead of being limited to -1 to +1. Normally distributed variables are not limited to -1 to +1 like a correlation. Now this is discussed in more detail in the DSEM section once again on slide 85, where all of this will become crystal clear. For now, we're just accepting that we can have a random residual covariance, i.e. a random correlation. Here's how you draw it on slide 34. Two outcomes, y and z, and we add a covariate x here to spice it up. So you have then a random variance filled circle for y on within, and a random variance filled circle for z on within, and then you have a random covariance or correlation. It doesn't matter which one, how you call it, but it's a random quantity here. So those three become circles, open circles on between, in addition to the random means that we already have here. So random mean and variance for the y variable, random mean and variance for the z variable, and then the correlation here. So suddenly now we have 5 latent continuous variables on between. Gets complicated quite quickly. And then we have a predictor, between level predictor of those latent variables. And they have residuals, and they are possibly also correlated. I didn't draw that. On slide 35, we have the input for this model 3 with random residual covariances or random residual correlations. You can say it in both ways. So once again, we have two-level random and estimator base, and we increase the minimum number of base iterations to 2000 here because it's a more complex model. And as always, we want to check Tech A to see that the convergence towards a so-called PSR value close to 1 occurs. Sometimes you need to have thinning, THIN, thin equals 10 is a popular value I often use. And then you usually can reduce the number of B iterations a little bit. Thinning gives you a better estimate of the standard deviations of the posterior distribution. So within we have all these random quantities, the random residual variance for PA, NA, and TI, and then these random with statements, which are the new feature of version 8.9. So what is that? Well, CPN, CPT, CNT, they are in the Fisher z-score metric. So it's a Fisher z-score version of the correlation, transformation of the correlation. So you can think of it as a Fisher kind of correlation between the variables. On between then, we talk about the variances here. We give labels for the means of the 3 residual variances, and we give labels for the 3 variances of the residual variances. And then we look at the means of these random correlations in Fisher metric. I give them the MC labels. And in model constraint then we can compute these new quantities, and we're going to focus on the median values for the 3 correlations, RPN, RPT, RNT. And as we will explain on slide 85 in more detail, we're going to look at the inverse of Fisher Z to get the correlation. So we go first, we translate the correlation to Fisher Z, but to get back to the correlation, we do the inverse transformation. And we're going to focus on the median, which can be expressed by a simple exponential expression here for each of the 3 correlations. So we put in the estimated means here in the formula, and out comes the median for the correlation. Here on slide 36 then you have the output for this model 3. You have on the between level you have the means, and we have then these 3 values for the Fisher transformation version of the correlation, those means, and they're all significant with these confidence intervals. And you have the variances as well. Once again, we're not going to be looking at means and variances together so much. We're going to consider distributions later on. But the one thing to note here, as the medians for these correlations, when they're brought back to the correlation metric, are similar to the means for the Fisher transformation, Fisher Z, means, approximately the same size and certainly sign. And that's a feature of this transformation, that for correlations that are in sort of in the range minus 0.5 to plus 0.5, the values are fairly similar. So it's not too far off to think about this in the correlation metric already up here in the Fisher case. So, okay. Now, slide 37 then. What do we do with this? Well, how about bringing in some covariates? So here you have then a regression of these random intercepts or random means, each on two covariates, SDQ, the childhood emotional problems, and the gender. And we'll also regress the residual variances on those, and now the new feature, regressing the correlations, the random correlations on those covariates. So we find that with the higher amount of childhood emotional problems, the positive affect is significantly lower. And we have another significance for a negative affect, the higher childhood emotional problems, the higher negative affect. Same thing for tiredness is also increased by SDQ. And the residual variance for positive affect is increased significantly. So it is for the negative affect, the variation in the residual variance affected. And we have one significant predictor of the correlation between negative affect and tiredness. Individuals with higher SDQ have a higher correlation between negative affect and tiredness. So negative affect is influenced in two ways, by the SDQ and also and so is tiredness, and so is their correlation, which could be interesting to try to explore substantively. All right, so that was one early example, and like I said, we're coming back to random correlations in the DSEM setting. So I'm asking here on slide 38 the fundamental question: why are these two-level models not sufficient for intensive longitudinal data, which is, after all, the topic of this talk? And we've gotten to that point now on slide 38. Finally, so what is lacking in the two-level analyses just presented? Model 1 has this expression, and we kept saying that this model accounts for correlations of observations across time using this random mean. So we are accounting for correlations across time, which is good, but there is further correlation to take into account. The residuals epsilon are likely correlated across time due to measurements close in time. So there's a second likely source of correlated measures across time. Consider, for instance, two time points t1 and t2, and the correlation between those residuals then is the function of rho here, correlation between the measures, and the distance between the time points. So the correlation between the measures is less than 1, as correlations are in absolute value. And the closer the time points are, the lower the power that we take the correlation to, so the higher the value. And for time points far apart, however, you take rho to the power of something big and it gets to be very small. But since the observations are close in time, the correlation between the residuals is likely to be high. So if we don't take that into account now for intensive longitudinal data, then we're making a mistake that especially may hurt the standard errors in the previous analysis, at least to some extent. Not all parameters, but for some of them. So why not model this correlation if it's so important? Well, we can do that, and there's a common way to do that. Lag1 autocorrelation, saying that residual at time point t is regressed or related to the residual at time points t-1 with a certain regression coefficient, certain autocorrelation. This was, for instance, done by these authors in 1989 in the Journal of American Statistical Association. So the important thing here, though, is not only does this take into account residual correlation, which is a more correct statistical model then, but it also offers substantively interesting modeling. This is the essence of DSEM. So how do we get there? Well, let's look at the last slide in this section. Why are these two-level models not sufficient? Let's look at the relationship to DSEM in detail. And although there are several formulas on this page, they're very simple, and I'm sure you can follow in the following steps. Here's the model once again, random intercept and residual. And now we're allowing for autocorrelation between the residuals. So the y's are correlated across time because they all are influenced by the same random mean, and also because there are strong correlations between adjacent time points as measured by the size of this beta coefficient. So that's our model. Now let's insert 8 into 7. So put this into 7. So we replace this by this expression on the right, and we get 9. Okay. Now, equation 7 for t-1 implies that epsilon for t-1 is equal to y t-1 minus alpha. You know, you say epsilon is equal to moving alpha over to the left-hand side there at t-1. So now if we insert that expression for epsilon t-1 into 9 here, then we get, let's skip the words, then we get equation 10, right? So epsilon here was replaced by this difference and put it there. And what do we have here? Well, we have the within level part of DSEM with latent variable centering of y at t-1. So we latent variable center our predictor. Think multi-level modeling where you do group mean centering. Here we do centering with a latent variable, which is actually preferable, the latent mean for this group, which is the individual intercept or mean. So that's what 7 and 8 implies. It implies 10. Although it didn't look like it at first. But then we can do a further step here, move alpha over to the left-hand side. The right-hand side doesn't change. And then we can just call this difference between the observed and the random mean for a within level part of the model, which is the within level variable. And same thing for the right-hand side. And this expression then is a relationship, the within level relationship in DSEM. There you have it. There we have the connection. So two-level modeling plus adding correlated residuals gives you DSEM. Not only do you get better standard errors, but this equation 12 is of key interest. And that describes the autoregressive features for this variable, taking out, accounting for the random mean into the between level box of the diagram. And then you can do this in a multivariate fashion where you have relationships across time, cross-lagged relationships between different variables. So with that, we are ready to start studying DSEM. On slide 40, we turn to DSEM analysis. So that is two-level analysis where we bring time into the model. I'm going to start with DSEM for a single outcome. And I'll call that step 3 in our 5-step analysis of the data. So we're considering two-level modeling using DSEM, a univariate analysis of positive affect. I'm going to take a look at 3 different ways to describe the model, and you may favor one over the other. First is a model diagram, second is statistical formulas, and the third is Mplus input. Over time, I think one changes, and Tiamer and I were talking about that the other day, and we're thinking of the models more and more in terms of the input itself. There are, of course, alternative ways to draw the model diagrams, and you will see different alternatives in the literature. There's always a balance between drawing them statistically correct and simple enough to capture it visually in an understandable way. Here's how I favor drawing it right now. So we have the within level variation over time, where we show a lag 1 relationship, PA at time point t regressed on PA at time point t minus 1. And when we have a between level part of the model, which is variation across individuals. So you have within and between. And the observed variable is decomposed into a within and between part in this way. The between part is a random intercept varying over persons, which is also referred to as a latent trait. So this model diagram is drawn in line with cross-lag panel modeling with random intercept, RICLPM. See it, for instance, in the Mulder and Hammacher paper from 2021. That's on our website under RICLPM. So we break out the between level random intercept here, influencing both time points, and show it explicitly influencing those variables. So let's step back for a second and ask ourselves, what's different in this drawing from the regular 2-level drawings that I showed in previous slides? Well, first of all, we have 2 time points drawn, which just exemplify a sequence of time points. It's just a slice of time. We draw the adjacent time points. If you want to, you could put ... here on the right and on the left. ... meaning it continues backwards and forward. And also, a second point is that compared to the regular multi-level modeling that we talked about, 2-level modeling, is that we draw the residual relationship explicitly in the figure here, exemplified by the within part of the model. Now, there's several conventions then in drawing this that are sort of implicit and become second nature after a while. First of all, what we mentioned is that we only draw 2 adjacent time points, t and t minus 1. And the second is that we draw the observed variables outside the within and between boxes, because they're neither within only or between only variables. And the second or third thing rather, the regression coefficient for the observed PI variable regressed on the latent between PI, on the latent within PI, are all fixed at 1. So these arrows all have coefficient 1. And also the residuals are 0 for the observed variables, which means that the observed variable is the sum of the 2 latent variables, reflecting the within-between decomposition of the observed variable. So any variable here is influenced by 2 sources, the between plus the within, with weights 1. Between plus within, very simple. Just a decomposition, no residual up here on the observed variables. The latent within level PA variables have residuals, and we've drawn that here. So there is where the residual ends up. Now, note also the last convention here, that the full within part of the model is shown only for the later time point, for this time point. We have a residual also for the earlier time point, but we don't draw that. So everything in the model, for instance, or later on a random variance, is drawn for the last time point here, but it exists throughout the series, going backwards and going forward. It's just a convention. Now, if you look at that from the point of view of formulas, relating to where we ended up just before we turned to DSEM, where we ended up in our discussion about regular two-level modeling and what was missing there. We talked about the observed variable being expressed in terms of a random intercept, alpha, which is labeled PA in the between box in the diagram, and a latent variable centered PA IT minus 1. So we have this latent variable centering here once again, and that is the latent variable centering that is the key to the analysis, avoiding the so-called Nichols bias, which is discussed in the original paper of TMR in 2018, Asparahov, Hammacher, Muten. If you want to read more about centering choices, you can read the Hammacher-Grossman 2015 paper in Frontiers of Psychology discussing centering in general. But latent variable centering is the key. And just like we did in previous slides, we can move this alpha over to the left-hand side here and define a latent variable which is the difference of the observed minus the latent between, and we call that within. So then we have the within part of the variable is beta times the within part of the variable at the previous time point plus a residual, which is exactly what we have up here. This is PA within for time point t, regressed on PA within time point t minus 1 with the regression coefficient beta and residual epsilon. Now we're going to stay with the fundamental issues here a little bit longer. The third way of looking at this model is through the Mplus input, which is very simple. In the model command you have the within and between parts of the model, because it's two-level, and you say on within PA on PA ampersand 1, so a lag 1 variable. So this regressed on that, and it's a lag 1. You can have lag 2 as well here, of course, but this is the simple model. And then you have variation in PA also on between. You don't have to mention the residual here in the regression. That's a default. That's included already by default. Now the within level slope, this one that we called beta in the previous slide, that's the autoregressive feature, as well as the residual variance, can be random, that is individual specific, varying across people. And that would then add latent variables to the between level. This is what varies across people. And note that Mplus is much more general than what it looks like here. It actually allows a full structural equation model to be specified on each of these two levels, within and between. So for instance, you can have a mediation model on within and on between. You can have a factor analysis on within and on between. You can have a full structural equation model on both levels. But we're going to keep it simple, fairly simple throughout most of this talk. Now, we should recognize that there are alternative ways to draw these DSEM model diagrams, and in fact, I draw them differently in the Mplus User's Guide. You've probably seen this drawing here in a simple case. The random, we have a regression of PA at one time point on the previous time point, and we mark random effects like a random intercept here, regression, y equals a plus b times x. You have the random intercept, or the intercepts rather being random, marked as a filled circle on within, which then becomes an open circle, a continuous latent variable on between. That's very simple visually, but it's not statistically correct because we never regress the observed variable at one time point on the previous time point. It's a within part of it that we regress, and also we do a centering here. But it gives you the general idea, but not very precisely stated. Now, Ellen Hammacher has a different way of doing it, which is statistically precise. she emphasizes decomposition into within and between level variation. So first she considers a decomposition. What I talked about before, the observed variable is a sum of the between part and the within part. Here with coefficient 1, again, just simple sum of the two. Whereas where the within part has subscript t, but the between part does not. It doesn't change over time. And then for the within part, she has a model, this same model, regression on within with a residual drawn for the last time point, and then between part like that. So that's a nice way of drawing it as well. Now, the style that I've chosen for this web talk, which I like, is compared to the user's guide style, there is no filled circle for the random intercept. And instead made clear that the regression is for the within variables, implying latent variable centering. So no filled circle. Instead, we have the between part of the model drawn as influencing the observed variables. So that implies, since it has unit loadings or unit coefficients here, same coefficient 1 across time, it implies it is a random intercept. And we see it very clearly then in the drawing, and we don't have to work with any filled circles for that. We pull that out separately. Now compared to the Hammacher style, there's no decomposition drawn, so it's simpler visually from that point of view. And the role of the between PA as a random intercept is instead emphasized. So in the Hammacher drawings, you don't have this connection. And there are no W or B superscripts for the variables, but instead the variable names match those of the input. Now, it's interesting that this style of drawing it is actually done in Hammacher and Mulder's work when they talk about RICLPM, but Hammacher decided not to do it for DSEM. So there are pros and cons of these different diagram styles, but just want you to be aware of them. Going to slide 48 then. What defines a DSEM run in Mplus? And I'm often using the term time series analysis. DSEM to me is multi-level or two-level time series analysis, or cross-classified time series analysis, as opposed to regular two-level analysis. Well, the key thing is this lagged option, triggering DSEM by allowing the ampersand, the lagged variable. So if you go back one slide here, it is this relationship can only be written out in the model command if in the variable command you have specified lagged. So it's the feature of talking about several time points in the model and several lag time points in the model. Then you can access the general modeling of lagged variables, lag 1, lag 2, etc. We talked about the T-interval option earlier on, and that can only be used if you have specified the lagged option in the variable command. Now T-interval is not necessary for lagged, but not using it would assume that time is simply 1, 2, 3, which is maybe not what you want for your data. Now before we get into the analysis with this model for the data, we need to talk about stationarity a little bit. Now, stationarity of the time series sounds like a complex statistical matter, but one can simplify it and just think about it here now for this model as implying that the mean and variance of the outcome are time invariant. That sounds a little bit restrictive, but it's not really a modeling limitation, but a necessity so that the model matches the data that we're considering. I'll tell you what I mean by that. So without variance stationarity, data would have values that explode over time due to increasingly large variances. So it's data with exponential growth. That is not data that we typically see in our applications. And we will take a look at that, take an example of that. Now just look at this bullet here. If you consider this AR1 model, that is lag1 autoregressive model on the within level, dropping the W superscript and just writing it like in 15 here. Stationarity for the variance, assuming residual variance is theta, which is the same across time. Stationarity implies that the absolute value of this regression coefficient needs to be less than 1. So an auto-regression, auto-correlation slope less than 1. Now, what if that is not the case? On slide 50, I take a look at stationarity versus non-stationarity more explicitly. So we consider this expression on the within level, PA at time point t related to PA at time point t minus 1, with autoregressive coefficient beta and the residual epsilon. Now, we can ask, what is the variance of that expression? Well, it's the variance of the first part plus the variance of the second because they're uncorrelated. But what is the variance of the first part? What's the variance of PA at t minus 1? Well, here, that's not easy to say. But here we can use the stationarity, which implies that the variance at t minus 1 is the same as the variance at t. So the variance of PA at t is the same as the variance of PA at t minus 1. We take the variance of that part. And that makes it possible to solve for this variance. You move this term over to the left and divide by 1 minus beta squared, and here you come out with this expression. Theta is the variance of epsilon. And if beta is absolute less than 1, then that will be a positive variance. And there you have it. That's a variance on the within level that we don't print in the Mplus output. We only print beta and theta, but we don't print the total within variance. But through model constraint, you can express this if you're interested in it. And we're going to show how we do that to compute the interclass correlation. Now, the variance stationarity also implies that these unstandardized beta coefficient, regression coefficients, are the same as the standardized. Because the standardization means that you divide by the dependent variable standard deviation and multiply by the independent variable standard deviation, and since they are the same, they cancel out. So that clarifies things. Now let's take a look at the opposite situation, non-stationarity of variance. So let's consider 10 consecutive time points, and let's say that first time point has variance 1. We're going to see how the variance develops over time when we don't have stationarity. So the variance at the second time point then is the expression, the second time point is by this formula here, is beta times PA 1 time point earlier plus epsilon at that time point 2. And that will be the square of this beta times the variance of time 1, which is 1, plus residual term, which we assume are going to be small enough here not to stack up against the beta term. Same thing for the third time point. Then we take the expression here, variance of that, which is PA at time point 2, time where we multiplied that by beta and add a residual for time point 3, and then we get beta squared, and the variance of beta squared is beta to the power of 4, where the rest will be even smaller relative to this term, etc. So then, going to the variance of the 10th time point is totally dominated by the first term, this term, beta 2, beta 4, and here it is beta 2 times 9. So beta to the power of 18. So for instance, if we have a beta of 1.5 that is not within the stationarity range, that would result in the variance at the 10th time point being 1.5 times 18, which is 1,478. So a very large variance, and you can then imagine if you generate data with such a model, the values would explode over time. Now we can also consider non-stationarity of the mean, which may occur with a trend over time. But then we could model that. We can use as a function of time as a covariate, so that residual DSEM, which we'll talk about soon, can be applied with stationarity for the residuals, for what's left after we have accounted for a function of time used as a covariate. So let's take a look then at slide 51, where we look at the input for this model 1. I want to add that the outputs for the key runs here are posted on the Webtalk site. So here we have then, we start with use variables. This is within the variable command. So up here you have the variable colon command name. And we select people that don't have more hours than they should in the data, and we get rid of some people that don't change in terms of PA over time. And then we include this lagged option, which triggers time series analysis, DSEM. And here we have lagged with lag 1. So we could add, could say 2 here instead to have a lag 2 model. And then a new feature in version 8.9 that I will talk about on the next slide is that T-interval is handled differently now for two-level analysis. And I'll specify that explicitly on the next slide. So here we take then the hours variable in the data and say that we want to use T-interval equals 2. And the new variable that is going to be used for the analysis is called time. So the user gives that variable name and can choose any variable name there. But hours is the time variable named in the data. So this two-level analysis using base and a minimum of 1000 B iterations is used here. And then the model is PA on PA ampersand 1. And we're going to label that R for reasons that will become clear. So that's the autoregressive coefficient. And PA is the residual variance in that relationship on within. And then we label the variance on between as well, because what we're going to go after here now is make the connection with intra-class correlation that we talked about in the regular two-level analysis. So we're going to compute two new parameters, the within variance and the ICC. So within variance is the total within variance, which is time invariant under stationarity. And that is equal to the square of the correlation, autoregression. This is what we call beta before, times the same thing, that doesn't change from the 2 time points, plus the residual variance, which means that this is equal to residual variance, what we call theta before, divided by 1 minus the square of the autoregressive coefficient, which we call beta before. So that's the total within variation. And then the ICC is the between variation, which we got here, up there, divided by between plus within, which is the total variance here. And out comes an ICC of 0.56, I'm not giving you, so we just summarize that fact here. And also in passing, once again, I want to emphasize that you want to use Tech 8 to look at the convergence, to gauge whether or not you need more B iterations to be sure that the PSR convergence criterion is staying close to 1 and not starting to drift up again. And we want to always use type equals plot 3 with base, because there are a lot of base related plots that we want to take a look at. And I'm going to show you that in a second. Now regarding T-interval, there has been changes in version 8.9. We've changed it so that it works the same way for two-level and cross-classified DSEM. So two-level has changed to the cross-classified style, which means that the initial missing values for an individual, if you go back to my T-interval discussion, you'll see what I mean, are no longer dropped for two-level, but are included. And that causes changes that are very, very small in the estimates. So you can ignore differences compared to past runs that you have done. But if you insist, you can get the old approach by adding the setting drop as a third argument in parentheses for T-interval. And also the original time variable, which is called hours in this example, is no longer changed by T-interval. We don't want T-interval to change your data that way for the analysis. But a new time variable that the user names is used in the analysis. That's time in the example. And that variable can be modified and defined if you want to. You can have functions of time, for instance, as a covariate. And if no new time variable is used and named by the user, then this underscore b int is used. Bin is what b refers to. Bin is the word that we used in the T-interval discussion earlier on. So here then finally we have the output excerpts for model 1 in this DSEM step 3. You have the within level results and the between level results. And on the within level you have the autoregressive coefficient here, 0.4. And you have the standard deviation of the posterior distribution, which, as I say here, corresponds to conceptually corresponds to the standard error for maximum likelihood. So therefore the estimate divided by the standard deviation is approximately a normal z-score. So you can think of it that way. But the confidence interval is a better statistic to report. That is, you should report this: lower 95%, lower 2.5% and upper 2.5%. So 95% interval, and it doesn't cover 0, which means that the coefficient is significant. So we give it an asterisk there. Now for residual variances here, or variances here. You can look at the variance here on between level. With base, variances are always significant, in the sense that the confidence interval, or credibility interval as the Bayesians call it, never covers 0. The Markov chain Monte Carlo algorithm keeps it positive. So what we do, Tiemer suggests gauging the importance of a variance by looking at the ratio of the estimate to the standard deviation, which is then an approximate z-score, and he argues for having it be at least 3 to be a substantial variance to care about. Otherwise, one would specify it as fixed, not something varying. And here, of course, this ratio is approximately 10, so there you have a clearly important variance that you need to include in the model. Same for the residual variance here. You also get the standardized results here, STDYX standardization, on the within level and on the between level. So you see here that on the within level, the regression coefficient is the same, standardized and unstandardized, and that's because of the stationarity. It wouldn't be so otherwise. And the residual variance on within standardized is 0.828, so the within level R square is 1 minus 0.828, so 0.172, which means that we have a lot of room to improve the prediction of positive affect by perhaps other variables, other predictors in the model. Now, slide 55 then, we can take a look at the summary of the results for this univariate analysis, DSEM analysis of positive affect, comparing the different time interval choices that we discussed in an earlier segment. So we have time interval 1, 2, and 3. And we can start with the time interval plot information. I'm going to show you a plot of this later on. And we talk about SMSE, which is a metric is hours, so it's a distance between the actual time and the time that we use in the analysis. And the average then, that average difference is very low, which is good, with t interval equals 1. It gets a little bit worse for 2, and more worse still for t interval equals 3. So this says that you're on average you have almost 2 hours time difference between actual time and time used in analysis. Whether that's seriously important in applications or not is depends on the substance of the analysis. You can also look at the maximum discrepancy for any one person at any one time point, and the maximum is 4.5 here. I think we print an error message if it's over some much larger value than that. I can't remember which value. Now the missing data coverage then is quite low for time interval 1. That is, we add a lot of missing data with t interval 1. A lot of missing data rows in the data. The coverage goes up for 2 and further up for t interval equals 3. This is not to say that these are problematic values. It's just that with this low coverage, you can have problems with more complex models. So I'm saying here t interval equals 1 matches the data best, but the low coverage, that is many missing data rows, can make convergence difficult for complex models, particularly random effects models. And then you can also take a look at the within estimates, the autoregressive coefficient, which is higher for close measurements than it is for measurements further apart. So it's natural that it goes down with larger distances here. However, we note that they don't go down according to the theory of lag 1, because 0.414 is not the square of 0.547 as expected. So that's just suggests that maybe lag 2 is needed in the model. As the autoregressive coefficient goes down, the residual variance naturally goes up to keep the total variance the same, stationary, as we talked about. The between level means don't change much, nor do their standard errors. Between level variance don't change much either. And we're going to come back to this kind of comparison of the different time interval choices, how they relate to the parameters in the model, a little bit further on in this web talk, and see how much of a change you have in a model that is richer than this univariate model. Before we start adding random effects to the model, let's take a step back and consider analysis of a single person. So we consider n equals 1 DSEM analysis, which is in line with classic time series analysis. For instance, you look at one unit, such as the city of Los Angeles and its air pollution over a long time series, looking for patterns in that time series. So we are looking at a graph like this in the univariate case. And here we're looking at a regression between observed variables. There's no longer a decomposition into within and between, because we're only looking at one person. And therefore, this is just a standard linear regression as it's drawn. We have an intercept, we have a slope, and we have a residual variance. So 3 parameters. So assuming that we have enough time points to estimate 3 parameters, this should be just fine. The estimate should be coming out okay. Of course, we can look at multivariate versions too, adding variables to the model. And a common example is the VAR model, vector autoregressive model, which is like cross-like panel modeling, except now for very long time series. And the interesting thing is that Mplus allows a full structural equation model to be specified, even when you're analyzing only a single person. So for instance, you can do factor analysis for one person, as long as you have enough time points. So what does the Mplus input look like then? Well, we're considering one variable, and we add use observations ID equals 41. So we're taking a look at person 41 in our sample. We still have the lagged option, and we still have the t-interval option. But we don't do type equals 2 level analysis. This is regular single level analysis. Estimator is still base, however. And the model then is a single model specification, single level model specification. PA regressed on PA at a previous time point, lag 1. Very simple to do. And on slide 57, and we'll take a look at the data for this person 41. Time series plot for 7 days, again the 7 days of Tuesday through Monday, and we have the PA score on the y-axis, and we see that the person has pretty level mood, positive affect mood for Tuesday, Wednesday, Thursday, and Friday, but then get very happy on both Saturday and Sunday, and less so on Monday. On the x-axis then, this person is observed through 79 time points, and there are 12 occasions per day with t-interval 2, so 12 per day for 7 days, max 84. So this person didn't record all the way up to that time point. However, even though there are 79 time points, only 46 of them are not missing. The rest is missing. So the effective sample size for this analysis is 46. But that's still okay, since we are analyzing or estimating only 3 parameters. Sample size 46 for 3 parameters should be just fine. On slide 58 then, we take a look at the estimates for these 3 parameters. So we see this autoregressive estimate 0.636, so that's a little higher than for the overall estimate for everyone. It is significant. Even though it's only for one person, we can find significance of it. And we get the intercept and the residual variance. Now once again we can ask ourselves, well, what's the mean of this person's variable, person's model, or variables in the model? Well, in the regular output we give only these 3 values, so you have to draw on your knowledge about stationarity. And the n equals 1 model has this equation, There's no subscript I needed because we're looking at only at one person. So the sample points are the different time points. So we have an intercept, which we call nu, nu, Greek, plus the slope, and then a residual. Stationarity implies that the mean at time t is the same as the mean at time t minus 1. We can call that mu. And therefore, we have the equation that the mean of that is equal to the intercept plus beta times the mean of that, which is the same. And therefore, we can move that over to the left and divide through by 1 minus beta, and out comes the mean, expressed in terms of parameters that are printed in the output. So in this case, it turns out to be 5.97, and that's seen actually in Tech 4 and the residual output. And I should mention that the variance that we talked about before, although it's not printed in the regular output, you can find it in Tech 4 and the residual. So you don't have to add the model constraint that I talked about, but you get the standard errors if you do that. So this person is on average 5.97, and we recall then that the mean for everybody was 5.76, so this person's slightly higher on the positive affect scale. Now the interesting thing is that, as is seen here on slide 59, you can do a joint analysis, n=1 analysis of all individuals, and summarize that conveniently in Mplus. So that can be done by using the data data command option type = Monte Carlo. And we describe that kind of feature in the User's Guide example 12.6, part 1 and part 2, how you set that up. So you analyze all the individuals in one run, and you get the estimates averaged by this feature. And you can see, check the Mplus input at this website, and that's a website that goes with a new book that I recommend, and at least the chapter here I recommend strongly for DSEM. So it's the Hamaker, Asparahov, Mutian, Dynamic Structural Equation Modeling as a combination of time series modeling, multi-level modeling, and structural equation modeling. Chapter 31 in the new second edition handbook of SEM. And in this section of that chapter called Empirical Illustration Part 1 on page 580 of the book, you will find a discussion of this joint n=1 analysis of all individuals. And it also then describes this type = Monte Carlo data command feature. You can find this chapter in the pre-publication version at this URL. So I recommend that chapter warmly, and I also recommend exploring n=1 analysis, joint analysis of all individuals, as a precursor to seeing which effects, which parameters should be random, should vary across individuals. You can see the variation across individuals in this fashion. On slide 60, I turn to step 3, model 2. And just to remind you, step 1 is the 2-level basic step. Step 2 is the regular 2-level modeling. And step 3 is the 2-level modeling, taking time into account in the model explicitly. And now we come to model 2 in step 3, where we want to add a random residual variance. And the reason we're doing that is because of our observation in step 1 in the between-level scatter plot of the positive affect variance and mean. We saw, first of all, a strong variation in the variance, heteroscedasticity, and a correlation between the variance and the mean. So if you look at the within part of the model, we have now put a filled circle for the residual variance going into the positive affect on within, and that means that that variance will change over individuals on the within level. So the within level residual variance will change, will be different across individuals. And that's what we model then as a continuous latent variable on between, and we let them correlate. So we would expect this correlation to be negative. And this residual variance can be interpreted as variation in what's sometimes called innovation or random shocks. That is, different people reacting in different amounts to certain events. And that then is the residual influence here that is different. Now, the random autoregressive lag 1 can also be added. There would be a filled circle on that arrow. We're not going to do that in this step. That's interpreted as inertia, so individual differences in inertia. How do we do the analysis in Mplus? Well, all of this is the same in the variable command. We use TINTERVAL settings that are the same, but now we add in the analysis type the word random, which then makes it possible to define a random residual variance for the positive affect variable, and we call that log v. And we discussed very briefly early on what that means, why we're talking about the log of that variance, and I will talk about it in more detail, more statistically oriented detail in a few slides. And that then becomes a random variable on between, where we let the two, the mean and that variance, correlate or covary. In this run, we're also going to use the save data command and save a file that we're going to take a look at in detail. So that's the file that will contain the variables used in the analysis, including what the time variable is that's used for the analysis by Mplus statistical machinery. On slide 62 then you see the number of time points here for different individuals, 240 individuals, they are the clusters. And we see here, for instance, that cluster ID 45 has 6 rows in the data, and it goes up to 83 rows, that is 83 time points for some clusters. And the mean lies somewhere somewhere in between. Now on slide 63, let's think about this and note that the number of time points per individual in a run using the T-interval option will include time points with missing data that was inserted by T-interval to synchronize the timing, and that's what we discussed in early segments of this talk. And then look, for instance, at the first individual on the list that we just looked at, ID equals 45, which has 6 time points. Going back here, 6 time points. But 4 of those time points have missing data, it turns out. To see the number of time points without the inserted missing data, you do a run without T-interval, and that's what we did in the step 1 Type Twolevel basic run. And there the data summary, if you go back to that, shows that this ID, number 45, is observed at only 2 time points. So 4 of the 6 have missing data that are inserted to synchronize. So ID 45 does not contain very much information for our analysis. And it is important to have sufficient number of time points without missing data when estimating random effects, such as regression coefficients, because the estimation is based on computing the random effect value for each individual, for which n is the number of observed time points. So that's in line with our n equals 1 analysis that we talked about. And here's a good paper that's on the DSEM special topics list of references. You know, special topics in the left margin of the Mplus homepage. Practical Aspects of Dynamic Structural Equation Models is a technical report that we keep adding on to when we get user questions that have not been covered in the report. Slide 64 then shows the results. And I actually included the model results first without log v here at the top. So that's just repeating what I showed you for model 1, step 3 model 1. And at the bottom we have with log v. So if you look at the bottom part of the table, which has to do with the log v run, then we see that the autocorrelation is changed a little bit, but not that much. And the residual variance, 0.483, is now a random variable, so it won't be listed on the within level. Instead, that variance shows up in terms of log v on the between level, the mean of that log v and the variance of the log v. And what we're going to try to do in detail here is translate that back into the variance, so going from log v to v. But for now, we're just going to observe that the variance of the log v has a positive confidence interval, does not cover 0, as variances don't in base. And we may take a look at the ratio of the two, as we talked about before, and that's clearly much greater than 3. Again, ST, the posterior ST, being analogous to the maximum likelihood SE, standard error, so that the ratio is analogous to a z-score, the z-test. So this is a substantial amount of variation in the log v. You may also want to take a look at this MBR article, an earlier article from 2015, where they talk about biases in the results when ignoring the random nature of the variance, of the residual variance. In that analysis, I believe there was also a random autocorrelation, which was a driver, really. That correlation was the driver of the bias. Now, to understand what's going on here with the log v and being interpret that to get a feeling for how big that variation is in the variance, let's take a statistical look at this. So the variance, we're talking about the variance of epsilon, the within level residual variance. And we, in Mplus, we specify that that variance has a log normal distribution. You know, it's a variance, so we want it to be greater than 0. And we know that variances have a skew distribution, a long right tail. And here is a plot of those kinds of log normal distributions for different parameter values. So it gets a particularly strong skew when the variance is large for the log normal. So this is and gets more normal looking when the variance is smaller. Now, because v has a log normal distribution, the log of v has a normal distribution. So that's why we work with log v instead of v, because Mplus wants all of its random effects to be in the normal distribution family. So that fits with the assumption of normally distributed random effects in Mplus. Now the log normal distribution for log v, or for v, the log normal distribution for v implies that v has median e to the power of the mean of the log v, which is printed out in the output. And the mean is the e to the power of the mean plus the variance divided by 2. And there's also an expression for the variance. And in some writing, you may see an equivalent way of expressing this, where you say that the variance of epsilon is e to the power of s where s is the variance, well, e to the power s, so that the variance is by necessity greater than 0, which we want, and therefore taking the log of that, log of e to the power of s is s itself, has a normal distribution. So that's another way of expressing it, except I think it's a little clearer to say that we make an assumption about the distribution of v, that it has a log normal distribution, and therefore the log v gets a normal distribution. All right, let's go a little bit further here. Repeating the picture, and I'm stating then that for a skew distribution, like the log normal, quartiles are better summaries than means and variances. You know, it's not like you can have plus minus 1 standard deviation telling you something away from the mean, telling you something important about the non-normal skew distribution. And interesting is that the quartiles can be obtained from the normal log v distribution, so which is the distribution we work with here in the program. And we can, for instance, consider quartiles 25 and 75, because half of the distribution lies between those quartiles, obviously, and that is 0.675 standard deviation from the mean. Because the log normal is a monotonic function of the normal, the quartiles, therefore, are obtained by exponentiating the normal distribution quartiles. And don't worry, I'm coming down to Earth after this excursion into the stratosphere of statistics, and on slide 67. So the quartile estimates and their confidence intervals are obtained by adding a model constraint run again with parameters from model. So we label on between the log v mean and the log v variance, and then we express these quartiles, the median being the 50% quartile and the 25th and 75th quartile, and they are based on the normal distribution, you know, mean minus square root of s. So in parentheses here is the normal 1 standard deviation below the mean, 1 standard deviation above the mean, and when we exponentiate that, we get the quartiles for v, for the variance that we want. And it turns out then that median v is 0.31, and with this CI, and that's a 50%. The lower 25th percent quartile for v is 0.15 with that CI, and 75th is 0.635. And we compare that to the non-random fixed residual variance in Model 1, which is 0.483. So that lies somewhere between the 25th and 75th. And we know that means tend to be overestimate, being high because of a long right tail. So therefore we want to consider a median instead. So median lies in between of these two, obviously. So how does that help us interpret this? Well, if you take the square, so these are quartiles on the distribution of v, the variance that we are interested in. So it's a variance, values of the variance at those quartiles. So if you take the square root of this and this, we get a feeling for how big the standard deviation is of the variance at these quartiles. And it turns out, you may want to scribble that the standard deviation here, then the corresponding standard deviation is 0.4 for the 25th quartile and 0.8 for the 75th quartile. So 0.8 standard deviation, which then can be related to the scale of the PA variable, which is 1 through 7. So it's 0.8, 80% of a scale step on the PA scale. That's the a typical or 75th percentile value for the standard deviation. So that tells you a little bit about how to bring it back to reality, after having been presented with log v means and variances, going via the quartiles and then taking the square root out of the quartiles. All right, enough about log v then. Let's go to slide 68 and take a look at Tech 4, because that has some new features also when we now work with type equals random. And just to remind you, we have type equals random because we are allowing for individually varying residual variances, so random variation across individuals. And we say then first of all that the within level covariance matrix changes over individuals when we have type equals random. So think about that in terms of the picture. The residual variance changes over individuals, and therefore the variance of PA on within changes across the individuals. So the variance of PA changes across individuals. And what Tech 4 does is to give you average over individuals for within. So you compute the variance for each person and take the average over that. So that would be down here for the covariance matrix, 0.642 is the average. It's going to be fairly close to the between level part of Tech 4. All of this is within level part, but not exactly the same. It's like doing repeated n equals 1 analysis and then taking the average. It's not exactly the same way of estimating it, but they are aiming for the same quantity. Now, what may be surprising, and here then for log v, we don't have any between level variation here. Sorry, we don't have any within level variation for log v. It's a between level variable. Now, still here, this may be confusing, the means for these latent variables appear on within. Usually they appear on between, but you know, each person gets their own log v value because it varies across the individuals. And this is the average of those log v values. Again, that's going to be close to the between level mean, the mean that you see on the between level in Tech 4 and also in the regular output. Same thing for PA. And here's PA ampersand 1 is listed as well. That's sort of unnecessary because they're going to be the same. And here too, because of stationarity. So that's a little tricky at first, and but I just want to make you aware of it. I don't know how important it is, but there it is. Slide 69 though. Slide 69 is a useful piece of information. If you remember in the input, at the bottom of the input on slide 61, we added a save data command, and where we save the file PA for tinterval2.dat, and that file is then the data that were analyzed. So the variables that were analyzed, and including the time variable that Mplus created. And the order format of the variables is as always listed, the positive affect first and the lag positive affect, and then the hours variable, which is in the original data, and then the underscore new time, which is the midpoint. I'll write it down here. Midpoint of time ranges implied by t-interval. It's only used in the time interval plot, which we're going to take a look at in a few slides. And then time, which is the variable that name that you give for the time that Mplus creates. You know, going from 1, 2, 3, the bin number essentially. Well, exactly, actually. Given by the user, created by time interval using analysis, same as the bin number. If you don't give any name, the default name is underscore bin t. So those variables, you may want to take a look at those and compare the original hours with the time that Mplus created, and see if there's a big discrepancy. On slide 70 then we take a look at some of the first rows of saved data for this person, ID equals 20 under time interval 2. And as you look at this, you want to compare with slide 14 showing in detail what t-interval does to the data. So what we have here is the original hours variable. The person sleeps, wakes up at 5, and is observed again at 7, 10, 11, etc. And the analysis time that you use in the computation is this bin time, just integers 1, 2, 3, etc. And new time, underscore new time, is giving you the midpoint of the bin interval that we're talking about here. And for instance, the problem here was for these time points for this person was that observed time point 10 and 11 ended up in the same bin, in the the 10 to 11 bin, which is corresponding to time 6. So we had to move 10, the earlier hour, into an earlier bin, the 8 to 9 bin, and therefore we get a misalignment between the actual time that positive affect was recorded and the time that is assumed by the new time variable. So you get the discrepancy here, 10 and 9. Whereas 11 stays in the right time bin, the 10 to 11 time bin, which is time 6. So you see then that misalignment at 10 a.m., 10 and 11 in the same 2-hour bin, 10 is moved to earlier. And as we're going to see in a few slides, this kind of misalignment can be looked at in plots. There's a so-called time interval plot for each individual on slide 72, where you see the observed time versus the new time, and you see the discrepancy, and the discrepancy is measured for each individual and each individual's time point. And we actually have a message warning the user of 2 big discrepancies. Now, one thing we can note here is that there's a lot of missing data then, of course, early in the morning and perhaps late at night as well. But that could be good to capture the fact that auto-regression between the last measurement in the evening and the first in the morning should be quite low, and therefore it's in a rough way takes care of the nighttime issue. But the nighttime issue is a research topic, and here we're only handling it in a rough way. You may also ask yourself if the nighttime autoregression is the same or different than a daytime autoregression for the same time distance. You can explore these things in the real data and perhaps try to incorporate it into the model. I don't know how much of a difference it makes in practice, but it could be worth studying. On slide 71, we turn to an overview of the plot menu choices. So when you are in the Mplus editor, you see at the top plot, and you click on it and you get view plots, and then you get this whole selection of plots to view. And here's the list given more clearly. We've looked at histograms, scatter plots, and between level scatter plots. Now for DSEM, we're going to be interested in time series plots. Time series plots is for each individual, each ID, and also another choice is the average over IDs. We also have the possibility of showing a histogram of the number of subjects per time point. So you can see the coverage per time point. And we're going to take a look at the time interval plots, which has to do with this misalignment in time that can happen due to the t-interval option. And then we have the three standard Bayesian plots, Bayesian posterior parameter distributions, which gives us the estimates and the standard deviation and confidence intervals for the estimates. And we have the Bayesian posterior parameter trace plots, which shows you the development of the parameter estimates over iterations, and Bayesian autocorrelation plots, which has to do with the quality of the variation in the estimates, what we would call in an ML setting the quality of the standard errors. We're going to take a special look at slide 72, the time interval plot for one person, ID equals 20. We've looked at this person before on slides 14 and 72, and you may want to go back and compare to those slides when you study this slide. So we're going to take a look at 12 occasions per day. That's t-interval equals 2, gives you 12 occasions per day, but we're only going to take a look at the first 2 days to make it simple. So we have 24 time points on the x-axis down here. And the time points on the x-axis represent the values of the time variable, the name that you give the time variable that's going to be used for the computations created by the t-interval option. So that corresponds to the bin number that we talked about before, integer values 1, 2, 3, etc. up. Now in this plot you have observed time in red and the new time midpoint, which shows you the misalignments in blue, I guess it is. So for instance, at time point 5, at bin number 5, which is the 8 to 9 time range, we had 2 times. We have we have observed time 10. Observed time 10. 10 was moved from the higher bin because we had an observed time 11 as well, and we had to move 10 down to an earlier time, so we got this discrepancy right here. And actually that's the maximum discrepancy across all time points, not only these first 24 time points, but across all of them at time point 5. There's none bigger than that. So there's pretty good alignment for this ID equals 20 when we use t-interval 2. And now the average, the SMSE here is the average discrepancy between the observed time and the new time midpoint across all the time points for this person. And that's what we say down here. And if we see some discrepancies also here for this is hours equals 16, where the midpoint was 17, so there's a discrepancy here, and hours 18 with midpoint 19 with a discrepancy there. You saw that on slide 70, I think it is. This new time midpoint is also the name of that variable in the saved data on slide 69 to 70 is underscore new time, just to orient you in this. So you can scroll through different IDs in these time interval plots and take a look at to which extent there is an important discrepancy between the red and the blue. And again, the maximum discrepancy is given over all the time points for a person and the average. Okay, going to slide 73 then. Here you have time series plots, and this time it is for the positive affect averages. So on the top left you have when you use t-interval equals 1, you have this pattern over time. This is for averages. And if you use t-interval equals 2, you get a pattern that looks more dramatic, but many of these extremely low points and high points are for a single individual. So it looks more dramatic than it really is. And when you look at this time series plot in the Mplus plot, you can actually hover or click on this point, and you can see how many people are in each point. I'm going to demonstrate that later. At the bottom we compare time interval 1 versus 3, and with time interval 3 we have a much smoother development, but you're almost lost the pattern here, so you would have to change the scale of the y-axis, which you can edit in the plot to see what kind of pattern there is. Now this is averages with different choices for t-interval. Now on the next slide, 74, we do a plot for 4 selected different people, and for t-interval 2, for the t-interval 2 case. That is the top right picture in the previous slide. So you look at this and you see a lot of holes here, which is missing time points. It looks a little bit like Swiss cheese here. A lot of holes in it, and some people have more dramatic development over time than others. So it's actually then hard to see a pattern in the data from any one individual. And the value of DSEM is that it combines information across individuals to get to see the pattern for the population, and you see it more clearly. And we're going to take a look at different ways of looking at that DSEM generated pattern. On slide 75, I turn to the plot menu option of between level histograms. And I'm going to show you 3 kinds of between level histograms for means. The first one is the observed sample mean for each person. So you take the average over time for each person and then plot the 240 persons in the histogram. Very down to earth and straightforward. Option number 2 is the model estimated between level mean for each person. So that requires the factors option of the plot command. Factors referring more generally to any latent variable, like a random effect in this case, the random mean. So the histogram in this case is based on the base estimates of each person's random effect value, average over 50 draws, as specified up here, from the posterior distribution of all parameter estimates. So that's the distribution that you have at the end when the analysis has converged. Posterior distribution of all parameter estimates, and in base the unknowns include not only the parameters but also the random effects that you want to estimate. This mean is referred to as B underscore PA for the PA variable, and there's also the median, of course. Now the third option is a cluster mean, which is quite different, although comes out quite similar as well. For each person, this is the average of the random mean over all iterations during the estimation. So that's a little bit different, based on different sets of iterations than number 2. And this approach is used in the output option residual parenthesis cluster. And it's referred to as PA, estimated cluster mean, in the between level histograms choice. Those choices are summarized on slide 76. So here are the 3 choices, and we are looking at the plot menu between level histograms, the third line here. And when you click on that, well, first of all, you see then that you have estimated factor scores in there too, because we have the factors option stated in the plot command. When you click on that, the window opens up on the right, where the first line is PA average over within, which is the first option. And the second option is this B underscore PA mean, or you can take the median if you want. The third option is further down here, and you don't see it in this window. So there you have the names and what they represent. On slide 77, I turned to between level scatter plots, yet another option on the plot menu. And I'm going to take a look at how the estimated cluster mean factor scores, the alternative number 2, relate to the observed average over within, the alternative number 1. I think number 2 rather than number 3 is the way to go. So using factor scores is the way to go here. So we see a strong relationship between the two, the observed sample values on the x-axis here and the cluster mean on the y-axis. Strong relationship as you would expect in a reasonable model. And this is done for 240 clusters, 240 individuals. And you can click on these points and it will tell you which individual is where. So we see some discrepancy here for some of these clusters, most likely due to missing data being handled better by the estimated cluster means as opposed to the sample means. In a bigger model, you would draw on information from other correlated variables in the model to do a good job for estimating the cluster mean factor scores. I say more about the estimation of factor scores on slide 95 in the context of multiple imputations, which is an interesting topic that I find quite a lot of practical uses for. And some of them are going to be shown in this talk, and some are going to be shown in a future DSEM talk. On slide 78, though, the last row in the plot menu here, like the variable distribution plots, is a useful plot as well. So that again requires factors in the plot command, and it's the same as we talked about, same procedure as we talked about in the alternative 2 for the mean. So it's the estimated between level mean, or median if you want, for each person using several imputations, several draws, 50 in this case, from the posterior distribution, that is the distribution after the analysis has converged, of all parameter estimates including the random effects. Now this latent variable distribution is created by the 50 draws times the number of people. So you don't take the average over the draws, but you use each of these draws. That gives a very smooth representation of the histogram of estimated between level means, the histogram that we looked at earlier. And it's an interesting idea, this imputation idea, that these random draws from the posterior distribution, they're also called plausible values. They allow uncertainty in the estimates to be accounted for. So if you think about this, it could be very useful for a single person, that you get not just one factor score, or factor score plus a standard error of that factor score, but you get a whole distribution of 50 values for this person. So a much better representation of the random effect for this person. And here then finally in the plot area, we can take a look at histogram of the estimated between level mean versus the latent variable distribution. So this was alternative 2, the estimated between level mean, and here you have the latent variable distribution, which is a more thorough going representation of this distribution. So you see the smoothness here, but it represents the same general shape. And it's a little bit non-normal. Normality is assumed in the model, like it is for every random effect, but the posterior updates this prior. The normality assumption is seen as a prior, so prior on the distribution, updates this prior to a posterior using the information from the data. So that gives you a feeling for what the real data looks like. On slide 80, we turn to the Mplus Runs that have been used in previous slides. We're going to take a look at the outputs with a focus on the plots that you can get. We're going to show the model from step 1, the type equals two-level basic analysis, with all the kinds of plots that you can take a look at there. And step 2, the two-level random regular two-level analysis. And then also the step 3, the two-level DSEM modeling, model 2 with random residual variance. I'm going to show plotting in Windows, but for Mac and Linux users, I want to remind you that Mplus produces a GH5 file from the plot command, and that can be used for doing plots in R. And here's the link to the web page where we show that. A new feature is that we've added a simple user interface for R plots with the use of R Shiny. So let's take a look at the step 1 type equals two-level basic run that we used in the segment 3 part of the slides. So we scroll down here in the input and we find that the analysis type is two-level basic. And looking further down in the output here, we get this warning of no variation within these clusters, that is no variation across time. So for positive affect, it's the familiar 4 clusters that we eventually deleted, the 4 people that did not change across time. A useful piece of output is in the summary of data further down. We check that the number of clusters is what we expect, 244. And then we have 2 columns, the size of the clusters, which means the number of time points, and the clusters, that is the people themselves. So 2 people are observed only at 1 time point, for instance. So we scroll down further here and see that it goes up to 49 time points as a maximum, and the typical value is around 20 to 30. Well, actually here the average cluster size is given, it's about 24. So the number of time points on average is 24. Here we also get the estimated interclass correlations for the variables. Positive affect 0.57 that we saw before, and negative affect and tiredness have approximately the same values. Let's take a look at the plots. So we look up here in the editor, click on that and click on View Plots. And then we get 3 different choices. Let's take a look at the histograms. And why not take a look at positive affect? So there's that familiar histogram. And now you can right click on that graph and we get the descriptive statistics. And the max value is 7. And 22% are at that max value out here. And we can go further to the next variable, negative affect with its strong floor effect, which is the minimum at 60% at the minimum. And going further then also to tiredness, it looks like that. And then hours looks like this. And this is a histogram then that you may want to change as we did in the slides. So we go in here again and get set up for hours. And now we're going to take a look at display properties up here in the tabs. And then the default number of bins is 20. Let's change that to 100. And click on OK. And out comes this familiar graph from the slides where the maximum should be on the x-axis should be 168, and we see that there are a couple of people here that go beyond that time point. So if we use the descriptive statistics, the max is 245, which is more than it should be. So that's the histogram choices. Now let's take a look at the between level histograms. So that's the average over within. So we take the average over the time points, and then that becomes a between level variable. So that is a can be shown in the between level histogram. And we see then this distribution that we had in the slides. And right clicking, we find that the max value has only 2% in it. So it's far less skewed than the individual level histograms. Let's take a look at another plot. How about the between level scatter plots? And here, let's take a look at the, we have PA, average over within, on the x-axis. Let's take a look at PA variance over within on the y-axis. And then you get this display that we saw before. And we can again hover over this point here or click on it, and it will confess that it is cluster 414. So person 414 is an outlier here with a low average and a low variance. And now there are several ways you can edit this plot, but I'm going to show that then in steps here. First of all, this is the legend plot, and by clicking on it you can move it, and having clicked on it you get this jagged edge of it. If you right click on it now, you can go down to properties, and on properties you can choose the font style tab, and you see then the size is 12. Let's up that to 14, say, and you click on OK, and then you see this increasing here, font size, but it falls outside of its frame. So you search for the edge here and get this arrow, so you stretch it out sideways, and you can do it downways too, to fill it so it can be seen properly, like that. And then you click somewhere else and it stays. Now you can do editing of the axis as well, the y and x axis. So that you do by axis properties. So you edit that one, and you see there at the top you have x-axis title, labels, y-axis title, labels, and the axis range. So for instance, if you want to increase the font size of this x-axis title, change font, and you can go down to 36 could be a good one. Click on OK, and click on that OK also, and you get this bigger font down there. And the same thing for the y-axis, and the tick marks here, the values can also be enlarged, and the length of the axis y and x and y could be expanded or contracted as you want to. Now right clicking again, then what do you do with this? Well, you can export the plot to a JPEG. Click on that and give it a name, and you can also save the plot data if you want to for analysis of the plot data in some other plot software. So those are the basic things that you can do within the Mplus editor and using the plot features. Here you see a list of key analysis that I used for Webtalk 6, and they are posted on the Webtalk 6 website. So you have the step 1 analysis, the 2-level basic that we just talked about, step 2, 3, 4 down to 5. Now step 2, if you remember, is a regular 2-level analysis that does not explicitly take time into account. So I include it for pedagogical reasons to contrast it with the DSEM analysis that follows. But let's take a quick look at this one, just to remind ourselves. You have then, in this case, no lagged or t-interval options in the variable command. It's a standard 2-level analysis. We add the word random because we're going to use some random effects here, random variances and correlations in this case. And therefore we're going to use estimator equals base, whereas in step 1 we use estimator, the ML, maximum likelihood estimator. So here we have the random variances, the residual variances, and the random correlations between the 3 variables in this case. And we do further modeling on between. So in this case, the plot command will show you between level histograms, scatter plots as before, but also the 3 Bayesian type of outputs: posterior parameter distributions, parameter trace plots, and autocorrelation plots. But again, it's not a DSEM analysis, so instead let's go and take a look at that, which is then step 3. So step 3 here, we're going to go to step 3 model 2, which was discussed in segment 7. So that's 2-level DSEM, 2-level DSEM with a random residual variance. So the use variable list here is positive affect, and we delete some clusters, 4 clusters, and we reduce time to the max that was intended. So we have cluster ID, t-interval, and lagged. 2-level random, it's base, and we see then in the input also that I have this save data command to save the data that we talked about in the slides. But the first thing that I look at in a base run like this is I go down to the end and check Tech8. By the way, here you have the output for the saved file that we talked about. I look for Tech8, and here it is. Tech8, we show it like this. So we have the iterations up to 1000, and we have the PSR, potential scale reduction, and it goes down towards 1. Now, if I see that, I would probably double this in a serious run to see that this PSR doesn't bounce up again to higher values, but has actually settled on a value close to 1 in a long sequence. Now then, after that, I go back and take a look at the output in the beginning and get the summary of data here as before, and then I go down and see if there are any warnings here before the model results information, and there are no warnings here. So I go further to take a look at the model results in the unstandardized form within and between, where I decide on significance. And then in this case we also have the standardized results, because we have a random effect here. It's within levels, standardized estimates averaged over clusters, and then we have the between level standardization, and we have various kinds of standardization as we do in regular Mplus. Now, in terms of plots then, now we have used lagged and t-interval, so we can then take a look at time series plots here for the first time. And here we have then time series plot for positive affect by subject or means of a subject. So for instance here then you have subject number 1, and here you can go forward to next subject, or you can go to a specific subject. How about our favorite subject 20, and take a look at that. Or you just go for the mean of the subject and you get this plot. And then you can actually then see how many people are at these extreme values here. So at this low value it's just one subject, like I was mentioning before. Same down here, one subject. Okay, show up, there you go. One subject here also, and here, and I think one up here too. So those, you can then see how much attention you should pay for the pay in terms of these low values. Maybe they should largely be ignored. Now the time interval plot here is then giving you, I haven't looked much at the histogram of subjects per time point, but the time interval plot is a useful one for looking at this discrepancy between the observed time and the time that we use in the analysis. So then you have that discrepancy between blue and red dots here. And you see that the max discrepancy for each individual here. And here you can plug in a specific individual. Let's say 41 is one that we have used before. And anyway, then how about the latent variable distribution? We have the usual base plots here, but what about the latent variable distribution? What should we expect to find there? Well, we have two random effects. We have the random residual variance log v, and we have the random mean. So log v, then starting with that, this is what the distribution looks like. That's the posterior distribution of the log v. Skewed. You have the non-symmetric, 95% non-symmetric credibility intervals, confidence intervals. You have the mean, standard deviation, median, and mode of the posterior, and these limits. And then going forward to the next person, here's the between mean, which is quite skewed as well. I mean, we saw the distribution of it in our slides as well. I also wanted to show you an output option that is useful for looking at factor scores. So this is again the step 3 model 2 DSEM with a random residual variance. So if you look at the output command here, you have a new option called FSComp. So that's factor score comparisons. And if you scroll down then to let's see, here we have between level factor score comparisons. And what you have then is for each random effect, in this case we have the random residual variance log v, and we also have the random intercept, of course. You have a ranking cluster and factor score columns that are repeated in sets twice here in the columns. So the person with the largest random variance in the log V metric is person number 36. And then you can see how far away the others are from that value. And scroll down and find the last person, the smallest value, being over here to the right for person 466. And you have also results for BPA here, that is the random intercept. And first, the person with the largest factor score on that is person 466 with the value 6.983, very close to the maximum of the positive affect score, score maximum. And the smallest is person 414. I think we've encountered him or her before, with a value of 3.076. So that can be a useful option when you want to look at the details of your participants. On slide 81, I turn to Twolevel DSEM for two outcomes. And that will then lead us into our DSEM analysis. Slide 82 shows a step 4 model 1, step 4 being bivariate modeling in DSEM. We can take a look at a cross-lagged analysis of positive affect as well as the tired variable. So you have the positive affect variables here and tired down here, and on the within level then you have the cross-lagged effects from one variable to the other. And the between box will then contain the random intercept for the two variables. For the within level then we have PA regressed on PA at the previous time point as well as tired at the previous time point. So these two effects. And likewise for tired we regress that on PA and tired at the previous time point. And on between then we model the covariance between the two random effects. Later on we'll add random effects for all of these relationships. So here now we're looking at standardized within estimates. You know, there are many kinds of estimates: standardized, not standardized, within, between, and one has to pay attention to keep track of this quite carefully in this DSEM analysis. So we're working with t-interval equals 2, and the standardized within estimates are like this. So PA regressed on PA at the previous time point has an autocorrelation of about 0.4 like we saw before, a little bit lower now. PA regressed on tired at the previous time point is negative, so if you were tired you tend to not be as positive in your affect at the later time point. But it's a fairly small effect. This is a standardized again, so we can gauge or judge the size of it. It is significant. It stays away from 0 up here. It is significant. It does not cover 0. But it's fairly small. And even smaller is the effect from PA on tired. So tired regressed on PA at the previous time point is almost non-existent. And that is not significant because that interval covers 0. So having a positive affect one time point doesn't make you more tired or less tired at the next time point. So one can speculate then, is the small effect of tired at the previous time point on PA due to the fact that what's more relevant is tired at the same time point. If you're tired at the same time point, will that lower your positive affect? So question is, would you have a larger lag 0 effect? We're going to turn to that in a while. But first, let's see if we get any change in these quantities if we start adding random effects. On slide 84, we take another look at the bivariate analysis of positive affect and tiredness. And in this case, I will add all possible random effects and add covariates as well. So if you take a look at the within level box here, you see several filled circles corresponding to random effects. We have a random autocorrelation for PA, a random autocorrelation for tiredness, a random slope for tired on PA, and a random slope for PA on tiredness. In addition, we have a random residual variance for PA here in the log V metric, and a random residual variance for tiredness in the log V metric. And now here we focus on a new feature, CPT, which is a random residual covariance, however expressed in a so-called Fisher Z metric that we will talk about on the next slide, which in most cases is almost exactly the same as a correlation metric. So ultimately, we will think about this as a random residual correlation. So all of these filled circles then become open circles on between latent variables, and we have 9 of them here, including the 2 random intercepts, one for PA and one for tiredness. So 9 effects. There are then regressed on, in this case, one between level covariate, a covariate that varies across individuals only, not across time, and therefore belongs inside of the between box. So this is possible, but I want to caution you that adding random effects everywhere you can be problematic. You can imagine if you include more variables here, the number of random effects is going to increase quite a lot. And although the base estimator in principle can handle random effects, you probably most often don't have sufficient data to support that kind of estimation. And you will run into convergence problems. You may not have enough time points for enough individuals in your sample. So on the next slide, we're going to take a look at how this random residual correlation comes about, and how to think about it and how to interpret it. Then let's take a look at random covariance, which is new in version 8.9. The model allows individually varying covariance, and in an earlier discussion of that in the regular two-level analysis, you can do this not only in the DSEM context. We wrote it this way, that is, the covariance is the product of the correlation times the square root of the variances, the standard formula for correlation. You draw on that. And we have sub I for all 3 of those quantities. The problem is that the correlation is not normally distributed. It can't be, because the correlation is between -1 and +1, restricted that way. So just like for variances, we transform it into something that is normally distributed. So we're looking at a so-called Fisher transformation, which looks like this. And that Fisher transformation is approximately normally distributed. Not exactly, but very approximately normally distributed, with a mean and a variance. And it's those quantities that we're going to print in the output for the estimates. The Fisher transform is actually based on trigonometry. It's an inverse hyperbolic tangent function, tan h -1 to the power of -1, -1 being the inverse. Now, it looks like this. So on the x-axis here you have the correlation varying between -1 and +1, and on the y-axis you have the Fisher z, which can vary from -infinity to +infinity. Here it's only from -3 to +3. So you do this non-linear transformation here to make sure that the correlation never goes below -1 or above +1. Now the reverse formula is rho equals this function of exponentials 2 times the z as argument for the exponentials. And that actually looks like bottom right. So bottom right we have Fisher z on the x-axis and the correlation on the y-axis. So you have this S-shaped function which looks very much like logistic regression, because we keep the values then between the y values between -1 and +1 here. So it's like a logistic regression, except then on the y-axis we have the probability between 0 and 1. But you can see it looks a little bit like the logistic regression equation. Not quite, but I wonder if Fisher was inspired by that. Well, he was perhaps more inspired by trigonometry. Now the median of the original row, and we're looking at median rather than means when we work with non-normally distributed variables, is obtained like this, plugging in the mean in the reverse formula. Instead of z, we take the mean of z. Fortunately here now, z and rho are almost identical for rho values, correlation values between -0.5 and +0.5. So very often we can think of the result for z as a result for rho. They're one and the same. And anyway, rho is not that non-normally distributed, at least not when the variances are smallish. Now this is discussed in detail in a new version of this paper from 2010, or technical report, Bayesian analysis using Mplus technical implementation. So now there's a new version, 2023, where section 9.1 deals with random covariance. So you can learn more about it there. We're going to see it in applications. Okay, so let's take a look at step 4, model 1 with all random effects. And here now we're going to bring in the x variables, the between level variables of SDQ, the emotional problem as a child, and girl, gender variable. And we're going to define girl as the gender -1 to make it girl versus boy. And then we're going to center SDQ, grand mean center, so that intercepts correspond to boy for the average SDQ. And now we have two-level random, where with so many random effects, we have 9 random effects, we better increase the B iterations to 2000, usually we work with 1000, and add thinning. So the within model then is the autocorrelation for PA and the log V residual variance for PA, and same thing for tired. And then the slope of PA on tired, PT, PA on tired, and the slope of tired on PA. And now we have also this covariance in the z-score, in the Fisher Z metric, PA with tired. So that's a residual covariance in the Z metric. And like we said, we're going to think about that ultimately as a correlation, because we're going to see values between -0.5 and +0.5. On between then you have the regression of all of these random effects, 9 of them, on the 2 between level covariates, and we let the residuals in those regressions be correlated, covariate, and we're going to label these coefficients, and the variance of them, the variance of these SPTs, SPT and STP, and the mean and the variance of the log V, and the mean of the Fisher-Z covariance value. Now, model constraint then we use to compute a couple of values. For instance, we might be interested in the standard deviation of the variance of SPT, and likewise for the variance for the tired regression. And we may also, for the log V, MPA and MTIA, take a look at the means of them. Actually, now I probably would use the median instead, and we talked about quartile as well in previous slides, using these expressions that we talked about earlier. And here we have the new expression for the median for the correlation between P and T, which is, now it is a correlation. We have back translated into the correlations. And the expression looks like this, just like we talked about on the previous slide. So I'm talking about this formula, the median here, using the reverse formula for rho. Now, with so many random effects, we should have some clear analysis strategies. So on slide 87, I point out that it's important to have a sufficient number of time points without missing data when estimating random effects such as regression coefficients, because the estimation is based on computing the random effect value for each individual separately, for which n is the number of observed time points. So it's like a n equals 1 analysis that it's based on. So if you have many individuals with few time points, that may complicate the convergence. And we talk about that in this practical aspects paper. It's a technical report that we keep updating. And the highlights of that is that convergence can be made harder by including individuals that do not vary across time. Well, we took care of that with positive affect. I didn't do it for tiredness. I should have, probably. Number of random effects should ideally be smaller than the number of time points. So 9 random effects means that we should have at least 10 time points observed for at least, I would add, for the majority of individuals, you should have 10 or more time points observed. And convergence problems can be avoided by building up the model in steps. First, starting with random intercepts only, adding random effects, looking for these z values greater than 3, the T-Hermer rule of thumb for their variances, and don't correlate the random effects right away. That also simplifies the analysis. Slide 88 then, let's take a look at the number of time points for each individual. Is the number of time points sufficient for 9 random effects is the question. And we're working with t-interval equals 2, so with quite a few inserted missing data rows. So the sizes of the clusters here is for the t-interval equals 2 analysis. Here we have it for the original data, which is what we obtained in step 1, Twolevel basic. So we see our familiar person 45 here, which has 6 time points, but we know that 45 over here actually has only 2 without missing in the original data. But we're more interested in people who look like they have at least 10 time points. 10 is more than 9. So 197, what about that person? Well, we find that person over here. That person has only 4 time points. So that's less than 9. 196 has only 5. 319 has only 4. What about 572? Where is 572? It's up here with only 2. 1,861, 2 as well. 456, 5. 415, 5. What about 357? Which we claim we have 22 time points, but not all of them are observed. So 357, well, there we're starting to get 11 above 10. So cut off somewhere here, then in sufficient number of time points without missing data. And since we have many more clusters going up to time points 84, I would say that a large majority of the clusters do have more than 10 observed time points. So we should be fine here. And that's what the analysis indicates too. Now another topic then, on slide 89, you have type equals random, a lot of random effects. What about standardization? Well, we have adopted this idea presented in this Psychological Methods article, where you do the standardization for each individual at a time using the individual specific variances. So it's analogous to n equals 1 analysis. You compute the standardized values for each individual, and then you present the average random slope, for instance, over the individuals. So the standardization is by that individual's standard deviation for x and y in the regression. And then we present the average random slope over individuals. Now, slide 90 shows that that often then leads to a so-called non-stationarity warning that we print. It looks pretty impressive, scary. Problems occurred in several iterations in the computation of the standardized estimates for several clusters. Let's see. Let's parse that sentence. Several iterations. Well, you know, since we want the standardized estimates, but we also want their distribution, that is, we want to be able to have confidence intervals for them, credibility intervals. So therefore, we have to draw this, compute this in every Mplus iteration for every base iteration. So in some of the iterations, we have problems for some of the people, some clusters. This is most likely due to autoregressive coefficients greater than 1, which we know gives non-stationarity, gives negative variances, so we can't standardize. So those posterior draws are removed, and the computations are built on the remaining ones. So the following clusters had such problems. So it looks like a lot, but then remember, it's only in some iterations for some people that in the posterior distribution of the for the autoregressive coefficient, it spills over beyond 1. Far fewer clusters would be mentioned when the autocorrelations are not random. Typically, this can be ignored, and that's described in this fact that we have here on slide 91. We have frequently asked questions, entry, standardized coefficients in DSEM or DSEM that you can find through this URL. Message can typically be ignored. Mplus handles it optimally, is what that fact says. Typical reason is random autocorrelations, where in some iterations for some individuals, some part of the posterior distribution is greater than 1. So the variance are negative under stationarity assumption, which means that the standardization cannot be done. It's due to small sample size or small number of time points for many individuals. And you can learn more about causes of this by doing n equals 1 analysis yourself for the different people that are mentioned. Or you can also examine factor scores to find clusters with large autocorrelations. And I'll show you later on how to do that. On slide 92 then, let's take a look at the estimates. And now we're going to take a look at unstandardized between level estimates. one of the four possibilities, within, between, unstandardized, standardized. So unstandardized between, and we regress on these two covariates. But here we're first looking at intercepts. So that would be the mean for boys at the average SDQ value. And on this slide we focus on the slope of PA on tiredness, minus 0.063. It's still a small slope on average. And this is for boys now. I think there were about 63% girls in the sample. So it is significant, but still fairly small. And we can also look at then the residual variance for that SPT, which is this down here. And it is not quite obeying the rule of ratio at least 3 here. It's, what is it, 2.5? And it's just barely above 0 for the lower confidence limit or credibility limit. I actually then also took the square root of that number, and it gives you then, if you take, so this coefficient, it has a normal distribution, and the random coefficient has a normal distribution. So here you can see how much above the mean of 0.063 you can, well, in this case it would make it slightly positive, that relationship, or if you subtract it you get it slightly more negative, but still it will be only what, minus 0.13 at one standard deviation below the mean. So it's still a very small coefficient. And the unstandardized non-random estimate, and it's the estimate I'm talking about is the slope of positive affect on t without covariate is minus 0.048. So no matter what, even with the random slope, we don't have much of an influence of previous tiredness on current positive affect. Now this was this was for the intercept, that is for boys at average SDQ. Now if you look at it overall, not conditioning in that way, you can take a look at the within level estimates averaged over clusters, and the within level specific standardization. Except here we carry out a trick. We use STD standardization, which refers to standardization with respect to factors defined by bi. And since there are no factors, this is then unstandardized in this case. But it's still the within level standardization idea, so it's an average over clusters. So here you can get the overall effect, not conditioning on the covariates. So you get the SPT here, slope, random slope P on T, and it's the small value comes up here again, it's reflected that way once again. So here the bullet says this trick is that the standardization has no effect here due to no latent variables, making the results comparable to the unstandardized between level estimates that we just looked at. And note that log V entries here are on the where do we have log V? Is on the variance scale, so positive values, no You don't have to exponentiate it, is what I'm trying to say. So typically we give them in the log V scale, but here we have already translated to the variance scale, so no exponentiation is needed. Another thing to note is that the standard errors of these cluster averages decrease as a function of cluster size. And very importantly, for significance testing of a random slope mean, the unstandardized means should be used, the estimates, not the cluster average standardized slope that we're looking at on this slide. So the significance testing should not be using this part of the output. So that was the story about the slope of PA on tiredness. Now let's go back to slide 92 and take a look at the random covariance or random correlation. So we're looking at unstandardized between level estimates, and the intercept here then for CPT is minus 0.193. So that is then, since it is in the range of minus 0.5 to plus 0.5, we can simply think of this not as the intercept for the Fisher Z, but as the intercept for the actual correlation. And it's significant, not including 0. And it's of a small size, but still perhaps important. And we look at the, and we see that the, yeah, it's significant, exactly, yeah. And we can take a look at the residual variance, and we using the TMR's rule of thumb here, the ratio here is certainly greater than 3. And that's the confidence interval for it. And the median of it is minus 0.191. And that's fairly close then to the mean, albeit for the Fisher Z, but we're saying they're the same, so they come out to be very similar. Now, on the next slide, then, CPT is minus 0.166, which is then average over clusters, so not conditioning on the covariates. And again, it's a small effect. But the question then is, do we have any interesting predictors of it to explicate this small random effect for the correlation? All right, that's a lot to take in. Basic knowledge needed for interpreting things correctly. So now let's take a look at the regression coefficients for the covariates. So now we are in the between box of the model, and we're looking at the unstandardized between level estimates. So here you have then the autocorrelation, RP, for autocorrelation for PA. No significant effects. We can actually scroll down then, and well, SPT, no significant either. Autocorrelation, we have an effect. So girls have a stronger autocorrelation for tiredness, is what this says. Significantly so. STP, no random effect, no significant effects rather. And the log V variance, residual variance for positive affect, that one is increased by the STQ increasing, the childhood emotional problems increasing. Nothing for the variance of tiredness, and in this case nothing for the correlation between positive affect and tiredness. We saw an effect of these two variables, background covariates, on one of the correlations in the regular two-level analysis, and that was for tiredness and negative affect. But negative affect is not part of the analysis here. Positive affect is diminished by increasing SDQ. We saw that earlier too. And tiredness is increased by that. All right. Now on slide 95, since we're bringing in a lot of random effects, we should also take an interest in looking at each individual's effect values. And that's the strength of this model. The random effect model means that you can look at, for instance, a cross-lagged effect for an individual based on the model. So we're talking about random effects, which we think of as factor score values. So here, to view, we have three ways to examine these values. One is to view the factor score distribution that we talked about earlier using the plot command with factors equal all 50, and using the latent variable distribution plot option in the menu. We showed an example of that. Second, you can get a summary of the factor score mean, median, variance, and percentile saved in a file together with the rest of the data, so that you could do a follow-up analysis of that. And that is obtained by the save data command using save equals F scores, factor scores. And you draw 50 of them, and here you can actually also do a thinning to get better results. And the third option is to get multiple imputations of factor scores and save all the between level information per imputation to be subsequently analyzed in a single level model, because just the between level then becomes the single level, using type equals imputation in the data command. And I've been using that quite a lot, and I find it quite useful, and we'll talk more about that in the subsequent web talk on cycles modeling. So here you use a save data command using save equals F scores. And now you may want to have more draws of it, and you have a factors equal list and a file name with an asterisk that you then use for a type equals imputation data type. And this refers to plausible values. And we have a technical report on plausible values for latent variables using Mplus. And here's the URL for getting to that. Now, we had number 2 here, save data command. Let's take a look at that. So on slide 96, saving factor score summaries. So here it says you use the save data command, save equals factor scores, and put them in a file. And what you have then is the original observed variables, and then you have the factor score mean for the random autocorrelation, mean and median and standard deviation, and a 2.5 percentile value and the 97.5 percentile value. And then you get the same thing for other random effects. So all of these factor scores. And you get the ID here at the end too. So you get the original variables plus summaries for the factor scores in this file. So let's see what we do with that. So here we said we wanted to do that to enable a follow-up analysis and a follow-up basic analysis of the saved factor score summaries. So I did that to look at a between level scatter plot of PA's autocorrelation. You know, we want to sometimes be sure that the autocorrelations are not too high for any one person. And here I'm looking at the 97.5 percentile, that variable. If you go back, it's this this value, RP97.5, that variable, versus the PA average. And so I have the autocorrelation 97.5 percentile here. Where is that for different people? And on the x-axis I have the average over within. And you see then that we have some quite high values. You know, percentile for a person can be either low or high. It's a high percentile, and when the high percentile is very, very high, then you're likely to get a non-stationarity situation. So if here you find one person, it turns out if you click on it, it's ID 414, and it sits out to the left here for a very low PA average. So it's a very unusual person. Low PA value. Perhaps this person has low PA over time, and the autocorrelation is very, very high. And the autocorrelation here is actually 0.97. So this is kind of person who can give us problems in the analysis. And it's also a very unusual individual. Perhaps we should consider it an outlier to be deleted. On slide 98, we turn to step 4, model 2, where we're going to add a lag 0 effect from tired to PA, so the same time point effect. But we still are going to have the cross-lagged analysis of PA and tired. So we have the cross-lagged situation as before, but now we have a direct arrow here from tired at time point t to PA at time point t. And that's easily added in the within statement, and that is we just mention the variable tired without any ampersand. That means the contemporaneous effect of tired on PA. But we keep the lagged effect to see if there is an important lagged effect still. And then tired is like before, regressed on tired at previous time point and PA at the previous time point. Slide 98, then you have the standardized estimates, both without and with this lag 0 effect. So the top part of the panel repeats what we saw before when we only used lag 1 effects, a small effect of tired on PA, small but significant in a standardized metric. Adding a lag 0 effect, we find that that is more than twice as big as the lagged effect. And now the lagged effect is insignificant. So what matters is how tired you feel now, influencing your positive affect, not how tired you were a couple of hours ago. On slide 100, we turn to DSEM. So I call that model 3 of step 4. So we're going to contrast DSEM with the regular DSEM. And we're going to consider the within level part of the model. So we have continuous latent variables here, all circles, on the within level. We're going to simplify the model that we talked about in the earlier slide. We're going to delete all of the cross-lagged effects and just talk about the contemporaneous effects, which were the big ones, or bigger ones. So we have then a simple model, PA on tired, that's that regression, and PA on itself, that's the autoregressive part or dynamic part of the model, and tired on tired and tired at the previous time point, the autoregression for tired. Now for DSEM, we changed the model. We no longer have these dynamic autoregressive relationships between the variables themselves. We still have PA on tired, but now we're going to instead consider the residual of PA after we've regressed on tired and say that that residual is regressed on the residual of PA t minus 1, which is the residual in the regression at the previous time point. So this is a linear regression for the residuals, so it has its own residual. And we do the same thing for tired. So substantively, this is a different thinking of the processes. PA on tired is specified like before, but this residual now is specified as PA hat, regressed on PA hat 1, which is one time point earlier. Same thing for tired. So our DSEM is more like regular two-level analysis, where we focus on regressing PA on tired, and we have no lagged effects, by which I mean these dynamic effects between the variables themselves, but instead we have auto-correlated or auto-regressed residuals at the top here, the hat variables. Now our DSEM is the same as DSEM if you have no covariance, as you can imagine, covariate being tired in this case. On slide 101 we compare the two models from a more substantive perspective. So DSEM on the left here, apart from tired influencing PA contemporaneously in both models, the two models say different things, have different implications. For DSEM, we're talking about an indirect influence of tired at t-1 through PA at t-1 to PA at time t. For our DSEM, it's only the residual of PA t-1 that influences the residual of PA at time t, and therefore PA itself at time t. So there's no indirect effect of tired to PA to PA. So two different interpretations. One, you believe that the previous value of PA influences PA, or you believe that it's only a residual correlation between the two, residual regression. So this is a regression for that residual, regressed on that residual with a residual. It's a linear auto regression of the residuals. And the two models do give different estimates of the regression of prime interest, namely the contemporaneous effect of tired on PA. There's a fairly small difference in this example, but that's not always the case. There's an interesting paper on this, comparison of models for the analysis of intensive longitudinal data in the DSEM journal. And the text around tables 6 and 7 is particularly interesting because it raises the question of whether or not you need to model the covariate here. You need to model the auto-regression or auto-correlation of residuals for the covariate under situations of missingness and under situations of different contextual effect. That is, when we have a regression of PA on tired also on the between level. This is all for the within level, to remind you. So the conclusion in those tables is that this is necessary to include for both DSEM and RDSEM to get correct estimates and standard errors. If you have missing data or if you have a contextual effect, that is the within regression being different than the between regression. So I recommend that paper. Now RDSEM is useful for many things. For instance, I've used it a lot to study the relationship between two outcomes, controlling for covariates that are a function of time, like a trend, a downwards or upwards trend, or a up and down trend, such as daily cycles. Now, with this situation of RDSEM, we can extend that a little bit. So we're looking at RDSEM here. You recognize it because there's no direct effects, no auto-regressive effects, only for the residuals. You can have a random slope for this relationship. And on between then, you will have 3 continuous latent variables, and you can regress each of them, the random intercept for PA and tired and the random slope on the 2 covariates that we used before, STQ and GRL. And the RDSEM input then for that fuller model would be like this. Still T interval 2, and we have these between level covariates, and we do the gram mean centering of the SDQ covariate, and it's 2-level random still, and the only difference comes in here. We have a random slope PA on tired, and we allow the residuals, the hat variables, to be regressed on each other for both PA and for tired. So no ampersands here on the right hand side, but instead hat variables, residuals being involved. And then you can regress PA and tired and S on the 2 covariates and allow their residuals to be correlated on the between. And here are the estimates. So here are the standardized estimates, and since we have and it's within level, and since we have random slopes, there will be the individually standardized estimates averaged over clusters, averaged over people. So let's focus on this PA on tired regression. That's the main thing here, and we see that it has a negative coefficient minus 0.199 on average, significant. And just to remind you, it was minus 0.193 when that coefficient was fixed. And on between, we see that S on SDQ has a negative effect, which is significant, and saying that as the childhood emotional problems variable increases, S gets smaller. S gets smaller. So there's an influence of SDQ on the random slope. So then you have to figure out what that means substantively. On the next slide then, we take the tack of trying out mediation. So we are interested in PA related to tired, and interested in PA related to, say, SDQ. But we are also interested in tired related to SDQ. So we have this little triangle here of an effect of SDQ on PA that's direct and indirect this way. So this is on the between level now. So we have mediation on between, PA on tired and the covariates, and tired on the covariates. And we can also add S on tired and covariates, and a correlation between the 2 dependent variables here. So the standardized between level estimates then would be PA on tired minus 0.435, and then tired on SDQ 0.228. So the product of those 2 would be the indirect effect controlling for gender. So that's 0.2 times 0.4, so that's 0.08, or maybe minus 0.09, which is then smaller than the direct effect PA on SDQ, the direct effect here. But that's how you can think about it, showing the facility of a mediation model on between, if you want to. On slide 106, I turn to a categorical outcome. I'm going to take the example of negative affect, where earlier we saw this histogram with a very strong floor effect, 60% at the lowest value. And we also see a sharp drop-off towards a long tail. Treating the variable as continuous will lead to model misspecification of linear models such as those used with DSEM. And that typically causes underestimated regression slopes. So the question is, what do you do with variables like this, which tend to appear quite frequently? Well, in this case, maybe you should just simply dichotomize the variable, or trichotomizes, using 3 categories. Or maybe you should treat it as censored, a continuous variable that's censored at the lowest point. or a two-part model, as we have described in Mplus Webtalk 4 Part 2, where I go through two-part modeling for both continuous and categorical outcomes. But censored and two-part really do require a little bit more people out in the tail. I don't think that's suitable in this case. So I'm going to stay with dichotomizing the variable. If you do that, you can fall back on the original paper by Asparahov and others in the DSEM journal, the original dynamic structural equation modeling paper, where there was a section on working with categorical y variables, where we assumed normally distributed continuous latent response variables that we call y star underlying these categorical observed variables. And when you do that, then you have a continuous variable for which regular linear models are relevant. So you apply DSEM to the y stars instead of to the y's. So then you are at least not making an obvious, clear specification error. The underlying normality of the y stars may be in question, but that's at least not as egregious as the assumption of continuous variable. I should mention that censored is not yet in Mplus DSEM. It probably will come. Two-part is in there. Nominal and count are not available for DSEM either. So here's an input for the binary case, dichotomizing NA. First of all, we delete a lot of individuals that don't change over time in negative affect. Many more people of that kind for negative affect than for positive affect. And then we declare as categorical a binary version of the negative affect variable. And we specify a lagged model for both the continuous PA and the binary Nabin variable. In define, then, we create the dichotomization by saying if NA is greater than 1, greater than the floor, then Nabin, the binary one, is 1. Otherwise, it is 0. An alternative to that is to use the cut function, cutting the variable at 1 and keeping the variable name NA. So, depending on how you want to proceed. So I chose the one that's bolded. And this is the same. The analysis is the same. And the model is just extended a little bit. So we do a cross-lagged model here. PA on PA ampersand 1 and the binary ampersand 1. So that's regressed on the y star for behind the binary at the previous time point. And then we regress Nabin on its previous value, the auto regression, and the previous value for positive affect. And then we correlate the random effects on between. Very simple to specify. And here are the results, standardized within level results. And just to remind you, the original NA treated as continuous would give you this result. That is, the cross-lagged effect of NA onto PA is very, very small and insignificant. The cross-lagged effect of PA on NA is significant but also very small. Higher the PA at the previous time point, the lower the negative affect on the next time point, but very small effect. Now, once again, those values are probably distorted by the misspecification of a linear model for this variable NA. So now when we dichotomize it instead, look at these effects. Much larger effect of the binary negative affect on PA, significant, and also larger for PA on negative affect. So there you avoid the underestimation and get more trustworthy results. So that's a simple remedy for a strong floor effect. Now, what about adding some random effects for this binary negative affect variable. Well, let's add random residual variances and a random correlation. How does that look? Well, we have this expression as before, and for both PA and NABIN, and we have the log V for PA, random residual variance. Now the binary NA does not have a free residual variance parameter. That's a piece of information that we lose when we have dichotomization. So we don't have any log V for the binary. And here then we have the correlation between PA and NABIN. So that's like a correlation between a continuous and a binary underlying variable. It's called a biserial correlation. So it's a random biserial correlation. It's actually the Fisher-Z version of that, but for small values it's essentially the correlation, the regular correlation. For small values of the correlation, it's the same. That's what I want to say. And here then you have just the covariances on between all these effects, 1, 2, 3, 4. And then we just label the means and variances and the means of that correlation. And in model constraint we can compute the mean of the variance or the median of the variance if we skip the second term. And we have the median of the correlation in that expression that we saw earlier. So you can do random correlations also when one or both of the variables are binary. On slide 111 I turn to cross-classified analysis. It's still DSEM, but it's a cross-classified version of DSEM. Cross-classified analysis is very useful for finding trends over time. And we do have some trends in our data here. That's shown, for instance, by the time series plot of the PA and tired, averages in the sample in this case. You have PA up here, jumping up and down a little bit. And you have tired, which shows a fairly systematic cycle over the weekdays of the time of the days. The sample averages, however, have varying precision over time, and the number of people for each of these time points varies for the different time points. So the question is, can we get a time series plot for model estimated values that better use the information in the data and take into account missing data as well? And the answer is yes, by cross-classified analysis. So on slide 113 I give a short summary of the theory for cross-classified analysis. And we're just looking at one single variable. So now we have two between-level cluster variables, person and time. So person is crossed with time, and in this case we have only one observation for a given person at a given time point. So that's a little bit different than typical cross-classified analysis in multi-level modeling, where you have, say, neighborhoods and schools, and you have several observations within each cross. Here we have just one. It's a generalization of the two-level model that provides more flexibility in the modeling. So therefore I call this step number 5, the last step in your analysis. Random effects can vary across not only persons but also across time. So the two-level model here with the random intercept can be written as a between person quantity, the mean plus variation across that mean, variation across people, and then you have the within person part. The corresponding cross-classified model has the between person but also between time random effect, and the same within person part. And here the between person alpha sub I and alpha sub t are each normally distributed and each have zero means. Now, it's a more flexible model, and you have full structural equation modeling possibilities in your model for both the within person, between person, and between time parts of the model. Now, the base Markov chain Monte Carlo algorithm, however, is more complex, as you can imagine, and is therefore slower. On slide 114, then, you have this step 5 cross-classified analysis of PA and tired. And here's where new things come up. You have the TINTERVAL, naming of the analysis of the analysis variable time that you give, and that then also plays the role of the second cluster level. You have ID and time, and you use type equals cross-classified, and you may want 2000 iterations at the very least, and thinning, and if you can, processors equal 12, which makes it a little bit faster than 8 processors on my computer. But if you don't have it, you'll be fine with 8, but you probably should get a computer that has at least the capability of doing 8. And the model is you do the auto regression for each of the two variables, and then we have that lag 0 model, PA on tired, and tired &1 as well, and then tired on PA &1. That's within. Now the between ID is then PA with tired, which means that you have variances for both and a covariance. But then we also have between time, and you have PA with tired, variances for both and the covariance across time. And note that we work with factors here in the plot command for future use. So on slide 115 then, I'm comparing the two-level and cross-classified estimates, and I'm looking at standardized within-level estimates. So at the top part of the model, of the output rather, we have the two-level results, and at the bottom we have the cross-classified results. And we find that they are very similar. There's no real reason that they should be different, and they aren't really different here on the within level. Now, what about the between level estimates? So you have then on the ID level, the ID between or between ID level, two level versus cross-classified, two level at the top and cross-classified at the bottom. Looks very similar in that case as well. So yeah, no important differences on the between ID level either. On slide 117 then I look at the between level estimates for cross-classified analysis alone, for the between ID level and for the between time level. So we have then the what's of particular interest here are the the variances rather for PA and tired. So these are the variances across individuals, and down here we have the variances across time. And we see that the variation across time for PA is rather small, and it's if you take this divided by 0.738, it's only 0.02, very small fraction of the between person variance. For tired, the fraction is a little bit bigger, 265 over 1.550, so 0.17 versus 0.02. So we have more across time variation in the tired variable. The covariance between PA and tired also is different, and the question is how you interpret that. That would take a deep substantive dive, which I'm not going to attempt right now. Turning to slide 118 then, I'm do again the standardized results for different t-interval choices. So you have t-interval 1, t-interval 2, and t-interval 3. And I'm going to focus on the within level results here. We notice then that, as before, that the autocorrelation effect decreases as the time interval increases. And that's as expected. Less correlation across time for the bigger time differences. But what's interesting is that the lag 1 effect here, tired, lag 1 on PA, goes down with increasing t-interval. So the time distance is longer, the effect gets smaller, also expected in a sense. And at the same time then, the lag 0 effect goes up as the t-interval goes up. So the contemporaneous effect becomes more important as the time interval increases. Now, it's not a huge difference here, certainly not between time interval 2 and time interval 3. So, once again, we're not that sensitive. The results are not that sensitive to the choice of time interval. Slide 119 then, I turn to plotting of estimated random effects. That's what we wanted to do to get a more trustworthy picture of the pattern over time, trends over time, and then we get from the average observed time series plots. So now we, with cross-classified analysis with cluster of ID and time, we have two between levels, and internally in Mplus they're referred to as level 2A for time and level 2B for ID. And therefore the acronym B2A is used for the between level factor score to be plotted. Between time level factor score to be plotted. So B2A is what we're especially interested in now as the new feature. And the plotting then is using the plot option factors equal and the plot menu option time series plots where when you have added factors equal, you get a last setting possibility here, estimated factor score, and there you click on B2A for PA and for tired. And out comes this. So this is for the 7 days, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday. And now based on estimated factor scores to draw on full information from the model and the data for PA and for tired. And we see then particularly how tiredness is low in the middle of the day and increases at the end of the day. Low, increasing, clear cyclical pattern. And it looks like we have the sort of the opposite for PA, where a low tiredness seemed to be maybe followed by a high PA, positive affect. Low tiredness followed by high positive affect. So we have something going on here in terms of a trend. It's not a linear trend of increase or decrease over time. I've seen that too, and actually in the short course video from the first day, topic 12 I believe it is, I have an example where there's a sharp trend, downward trend for, I think it was positive affect The question then is, how do you model these trends and cycles? Well, that's a long story, very interesting story, but it's a topic of a future DSEM web talk. But for those who can't wait for this future web talk, I gave some statistical background for cycles modeling already in 2017 in the Mplus short course topic 13 part 8, where I discuss a heart rate example. On slide 121, we're going to turn to the Mplus run for cross-classified. So we're going to take a look at plots for the step 5 cross-classified analysis of positive affect and tired. Specifically, we're going to take a look at the time series plot, where now in the cross-classified case, we have an additional possibility here of plotting estimated factor scores across time. Obviously, that can only be done in the cross-classified setting, where factor scores are produced across time. And they have labels B2A for positive affect and B2A for tired. And 2A corresponds to level 2A, the time varying across time between level of cross-classified analysis. And I'm going to tell you about some right-clicking options, putting in a mean line, average line, and timelines. So horizontal and vertical lines. And here's a little extra feature that I'm going to show you, a trailer for future web talks, where I'm going to show you a so-called loop insert to handle cycles. And that future web talk will also talk about weekday effects. But that's not for this web talk. Now let's turn to the step 5 cross-classified lag 0 run. And I'm going to do it with t-interval 3 here. So we have then the usual situation here for cross-classified. Type goes cross-classified, and we have a within part of the model, and a between person part of the model, and a between time part of the model. Now we're going to take a look at the time series plot, and we're going to be focusing on the last possibility here, the estimated factor scores, which vary over time because we have cross-classified analysis. And we're going to then take a look at the variables that we have available to us. We have the PA and tired random effects, and also the B2A PA and tired. I'm going to take a look at B2A for the first example here, and we see this pattern, which can be clarified a little bit if we right-click and show the mean line, showing that the mean is 0, as we expect for the between time random effects. They have a mean of 0. They get added to the other parts of the model. And if you right-click, you can also find a timeline option, and you can put in the timelines for, in this case, t-interval 3, which then has 8 time points per day. So we do an increment of 8 here. 8 times 3 being 24 hours of the day. And here you find then that you have day 1, 2, 3, 4, 5, 6, 7. So we've done that right. So this is Tuesday here on the left, and then Wednesday and Thursday going down a little bit in positive affect, and then up again for Friday and Saturday, very happy, and Sunday starting to think about Monday maybe, which is much lower down here. So you get that for the mean and for the median, and then for tiredness you have the same thing here. And then you can also hide the mean line, and you can remove the timeline. And well, that's about it for that analysis. I also wanted to show you some other plot features for DSEM related to time series plotting, which will be discussed in a future web talk. It once again draws on the time series plot, and we're going to take a look at the observed sample values, means over subjects. Here we have it for positive affect again, and we see somewhat of a cyclical behavior, also perhaps more pronounced for tiredness. For clarity, we can right click and insert timelines. Once again, 8 measures per day: Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday. Now I'm going to add a new feature. I'm going to insert a so-called loop plot that you set up in your, that you define in your Mplus input. I'm going to do it for tired, and here we go. So here we have a fitted curve that fits the cyclical behavior over time reasonably well. Not perfect, but reasonably well. Catch the lows and the highs, low and high. Tuesday, Wednesday, Thursday. Friday, we don't seem to catch the low. That is, people are not they're very low on their tired score on Friday, and even lower on Saturday and on Sunday. So Friday, Saturday, Sunday seem to be misestimated a little bit. So some kind of a weekend effect. Let's take a look at PA, positive affect, and insert the loop plot for that. And that captures the cyclical behavior pretty well as well. Tuesday, Wednesday, Thursday, but then Friday, they get more positive. Friday, Saturday, Sunday, and then Monday, of course, going down. So there is a way to catch this cyclical behavior. It wasn't a very strong cross-time effect for PA, but it certainly has a specific pattern here. So you can do this so-called loop plot using a certain sine cosine function, and to which you can then also add weekday effects to capture the weekend behavior. So we'll talk about that in the future. On slide 122, I turn to the important question of how large n and t have to be in your DSEM analysis. And I'm going to show you Monte Carlo simulations for both two-level and cross-classified DSEM. But first, on slide 123, here's a checklist that you may want to take a look at before you contemplate DSEM analysis. First of all, do you have enough time points? And we recommend at least 15 to 20. And if you don't have that, you might instead want to do a single level wide analysis. And you want a little bit more, at least 25, for good performance with random slopes and variances, the random effects beyond the random intercepts. That requires more time points. And at least 50 for good n equals 1 performance, although we saw that we had an example for one person with 46 time points, and that where the results look good for a very simple model, however. Now, another important question you're going to ask yourself is, do enough individuals have enough time points without missing, particularly in the context of using the T-interval option, which inserts missing data rows? And if you don't have that, random slope and variance estimation can be problematic. And also, does your outcome have variation across time? And that's, after all, the central part of your analysis, why you do the analysis. And you may want to consider deleting individuals with no variation. And do you have enough individuals for random effects modeling on the between level? You know, on the between level, you can formulate a full SEM model if you want to. And we recommend a minimum of 50 people but many more may be needed for certain parameters like between level variances. Variances are particularly hard to estimate well. And in the simulation that I'm going to show you below, I needed 500 people. And you should also ask yourself, does your outcome have a strong trend that should be modeled? If yes, use RDSEM with a function of time as a covariate. Now all of these points here on the checklist depend very much on the specifics of the model. And if you want to go a little deeper and get a little bit more of insight in what you need for your situation, you want to do your own Monte Carlo simulation. And it's not hard. On slide 124, I point out that some Monte Carlo work has already been done in this area by Schultzberg and me in 2018 in the DSEM journal. And we looked at 9 different kinds of univariate DSEM models with varying complexity. For instance, a univariate model with random intercept, random order regression, and random residual variance turned out to need 25 time points for a sample size of 150 and 50 time points for a smaller sample size number of people. Now, what is worse than, I'm quoting from the paper, having a lower n or a lower t? Can large n compensate for small t better than large t can compensate for small n? And it seems like large n is better. With that said, the random, autoregressive, and residual variances do need fairly large t to be well estimated. So if the autoregressive or residual variance is of substantive interest rather than just a heterogeneity feature to control for, many repeated measures would be needed. So there's a lot to learn from that paper, but your situation is still probably quite different. In the current study we have 240 people and an average of 24 time points. So by the rules up here, it seems like it would be sufficient for a univariate model, but is it sufficient for a multivariate model like the bivariate models that we have looked at? So we turn to doing our own Monte Carlo simulation. And we can do that if we have some initial DSEM work, initial DSEM analysis that can give us parameter estimate values that we can save by using the S values option in the output in the real data run. And I did that for the step 4 model 2, the lag 0 effect of tired influencing positive affect. So I put in the 250 observations and 25 time points, which is the average number of time points for the people. So the Monte Carlo command then specifies the, well, starting really here, 250 people observed over 25 time points, each one of them 25 time points. If you multiply that, you get the total number of observations. And if you make a mistake, Mplus will tell you. And I work with 500 replications. Often I start with 100 or even one replication. Usually I start with 1 to see that I specify the model correctly. And then I go to 10 to see that I get roughly the correct estimates. And then I go to 100, and then I do publication quality with 500. So here I have number of cluster sizes equal 1. There's only one size 25. I have the lagged option here, signifying time series analysis, DSEM analysis. And commented out here are various ways of saving all of the replications if you want to, or saving one replication if you want to take a look at the values for one replication. I do two-level analysis here, estimated base, the usual base specifications, and I have a model population and a model. And I usually just copy over the model population into the model section. So you have the autoregressive feature and the contemporaneous lag 0 effect here and the lag 1 effect, and you have the autoregressive for tiredness and the cross-legged effect for tiredness. And on between you have those coefficients. So all of these values then you get from S values and just copy in. So it's very simple to do. So what I found here, based on these estimates for 250 people, 25 time points, excellent results in terms of the parameter estimates, in terms of the standard errors, and in terms of the coverage. Now, if I went down to only 15 time points, well, I would call them good results. Not excellent, but good results. A little bit low coverage for tired's autoregressive effect, for instance. But not terrible. Going down to 10, not acceptable results. So this would agree with the checklist points that I gave you earlier. Now, a more realistic analysis would be obtained with varying cluster sizes. So we have individuals with different number of time points. Now, the real data has maximum 84 time points. This is with t-interval 2. An average number of time points 24. That's why I went with 25 here to round it off. Now, an approximation to this situation, one can do this in many different ways, but a very simple way to approximate this picture with people having different number of time points is to take, say, 5 cluster sizes. So here I say that we have 10 clusters of size 5. So that's a little low. Only 5 time points, particularly if you have a model with 9 random effects, but you want 10. You have 65 clusters of size 15, 100 clusters of size 25, so that's the average. 65 of 50 and 10 of 80. And I ran that then, so that's the same as n equals 250, but then varying number of time points from 5 to 80. Still have excellent results in terms of estimates, standard errors, and coverage. Now on slide 127 then, I bring in random slopes, random effects. So parameter values are then again using S values based on step 4 model 1 with added random slopes, random variances, and random covariance. So that's that model with many, 9 in this case, random effects that we talked about. So this is a more complex model. And I used 250 people and the 5 cluster sizes that I had on the previous slide. And actually I could get good results here, except between level variances have somewhat biased estimates. The estimates are too large, as you might imagine with a variance distribution with a long right tail. Biased estimates and biased standard errors. And it turns out that if I up this to 500, double the sample size, then those biases are, if not totally disappeared, they're gone down to be ignorable. Now you may not be that interested in these variances. I don't know. It depends on what the substantive question is. Now, in doing this, in doing simulations with random slopes, you have to be aware of an issue here. And we have implemented a new feature in version 8.9, which comes out when you ask for Tech 9, which you should ask for in Monte Carlo simulation studies. So in this case, it says 351 clusters were removed because the generated random effects produced non-stationary time series or non-positive definite covariance matrices. So with random slopes, variances, and covariances, non-stationarity is quite likely for some clusters in some replications. And that created havoc in the past in simulations in 8.8 and earlier. Those replications were deleted. So you could end up with, say, getting only 100 replications out of 500 that are summarized. So low percentage of reported replications. So that is not a very useful Monte Carlo study. Now, however, the cluster is thrown out that has this problem, the non-stationarity problem, but the replication is kept. It can be very few or only one cluster in a replication that has this problem, and that shouldn't hurt the whole replication. 351 may sound like a lot, but it's less than 1% of the total generated number of clusters. 250 clusters, so number of people, times 500, which is the number of replications. So this is actually an ignorable problem. And now we get 100% of the 500 replications reported. Now, what do we do with cross-classification? Cross-classified Monte Carlo. Well, that's not hard to do either. Once again, drawing on S values from a real data run. The specification of cluster sizes is a little bit more complex here. There's a bracket approach used, but it reads the same way. You have 10 clusters of size 5. We'd only draw one person in this combination of time and ID classification. 65 of 15, 100 of 25, etc. Just like before. It's just specified, expressed in a slightly different way. The number of cluster sizes is 5, and we don't have to worry about this number. You could have said 1 here as well, but that would take us deep into details of C sizes that you can read about in the user's guide. But 5 corresponds to the 5 different cluster sizes. So we do cross-classified analysis, and everything on the right here is obtained from S values in the real data cross-classified run that we did. It's the lag 0 run that we talked about. And I'm only giving model population here. You also have the model, which is just a copy of this. So you have PA on tired, the contemporaneous effect here, for instance. Now the new thing is that we have two between level 2A and 2B. And we touched on that a little bit when we talked about plots. And here is the key issue. In the S values from the real data run, it says between time. And that has to be replaced by between level 2A. So 2A is the time dimension. And between ID has to be replaced by between level 2B. So that you have to do yourself, changing that here and there. And this run also showed excellent results. No problems in the output. It takes a little bit longer, and therefore I went down to 100 applications. But of course you can do 500 easily if you just, say, run it overnight.